Go. So we've now started the recording for the first session today. So we decided to break up the session in two different groups. So there's call it a morning session and an afternoon session. The course today is going to be dedicated to bottom hole pressures, and it's a part of kind of like a course series that goes every single year where we try to focus on just very, very specific parts of Whitson Plus, deep dive into the theory and the associated functionality. So today in the course that we're going to go through, Stian is first going to do a theory part where we basically get a overview of not only the equations and the theory and the different correlations we have available, but practical things such as flow paths, artificial lift methods, etc. And then Mo is in this first session going to do the exercise part, and then in the afternoon session, Stian will still do the theory, and I'll try to do the exercise part and see how that goes. The course is recorded, as mentioned, so we'll distribute the recordings as a part of everybody that's in this group, and also everybody that is either a Whitson Plus subscriber or that is a part of the ongoing consortiums. So with that, Stian, I'll just give the word over to you. We'll try to have breaks every 45 minutes or so. Be a little bit depending on where it's natural, but we'll make sure to remind Stian about that. So Stian, just take it away.
Yes, thank you. Hello, everyone. Good morning, good afternoon. I guess we're in many different time zones in this meeting. Myself here in Stavanger. My name is Stian. I'm one of the senior software engineers in Whitson. I will walk you through the theory part of today's short course. It'll take about an hour or so. I hope you've grabbed a cup of coffee. This full disclaimer, there will be some equations, but hopefully they won't be too scary. So just a couple of general information points that Matthias has already gone through. It's after the course. It's supposed to be interactive. So feel free to ask questions in the chat. Matthias and Mo will track that and try to answer as fast as they can. I will also follow the chat while I'm talking and try to bring up questions in plural so that everybody and try to answer the best I can. If you want to speak up, that's also okay, but please try to remain muted when not talking so we avoid any background noise and these things. All the material will be sent afterwards. The presentation has already been sent out. There's probably been a couple of small fixes, so we'll send out a revised version after the course, together with the recording of this session. Yeah, some of it will be presented and talked about in detail. Some of it are more for reference, especially on the theory side. Some of the equations will sort of just, I'll talk a few sentences about, and then go to the next slide. And that's it. For the last part of the course, the largest part of the course, there will be an exercise where you all get to use the software and try out a bit of different things in our BHP feature. And to access that, you go to courses.whitson.com, not your own domain or your company domain, but courses.whitson.com. Use your email, the one that you have attended this course with, and the password to join is Whitson BHP 2023. And if you have any questions or any problems or difficulties, just send a mail to Matthias and he'll help you out. So agenda, we've already gone through, but for BHP calculation fundamentals, I'm going to talk a little bit about why we do BHP calculations, the input, the difference between single phase flow, how that relates to what it actually is, which is a multi-phase flow problem, the correlations that we use, a little bit about flow paths, different flow paths in the well, what kind of artificial lift methods we typically use, and finally the tuning of the BHP correlations. And then after the theory is concluded, we will go over to the exercises. Okay, BHP. So first off, what is BHP? Bottom hole pressure, or flowing bottom hole pressure, if you will. In Whitson Plus, that is defined as the well pressure at the depth of the top perforation, the top of the perforated interval. That's here. There are two reasons for that, one theoretical and one practical. The theoretical one is that this is the point at which you have the full mass flow of the well, the deepest point you can go in the well, where you have the full mass flow. The rates that you have recorded at the surface are flowing fully through the well down to that point. Along the perforated interval, there will be a change in rate. It may not be as stepwise and nice in this, but there will be some gradual change in the rate. That's the theoretical. The practical part is more to do with how the wells are in tight unconventionals. They're most often horizontal in the perforated interval. So where you place that reference point doesn't really matter that much. And if you don't believe me, you can test it yourself. You can always move the top perforation depth that you specify to any point along the well, as long as you don't place it deeper than the deepest point in the well deviation survey. So you have the depth there, and you have the deepest point in well deviation survey. And if you want to move the reference depth to, or the BHP point, the point where you calculate the BHP, any deeper than the top perforation, you can do that. But you will see that the difference is very marginal unless your perforated interval is a sort of some inclined angle or vertical. But typically that's not the case in tight unconventionals. So why do we calculate BHPs? Because we generally don't have gauges to measure it. And we need it for many things. Was there a question? Okay, sorry. In DCA, we don't use it per se, but the assumption there is PWF is constant, flowing material balance needs bottom pressures, rate transient analysis, both analytical and numerical, and most complicated kind of reservoir modeling, which is numerical modeling, also relies on bottom pressures. What are the inputs to a BHP calculation? So we need the rates, and strictly speaking, what we're talking about then is the so-called surface rates, and that's produced volumes at some specified pressure and temperature, standard conditions often, which we typically define as 14.7 psia or 1 atmosphere and 60 degrees Fahrenheit. We also need to know the pressure at the outlet of the well, if you will, the wellhead pressures, or in some cases, if you have a tubing string and a casing, you will have two pressures. You have one that measures in the tubing and one that measures in the annular space, the tubing head pressure and casing head pressures. And we need to know the temperature at the wellhead, both inside and of the surroundings. I'll get back to why. But those are the inputs on the production data side. On the well itself, we need to know how the well looks. That's expressed through a well deviation survey. How deep is the well, where's inclinations, etc. And we also need to know the perforated interval. So you typically have a vertical section down to a horizontal section where the fracs are along the perforated interval, highlighted with this thick blue line here. We also need to know something about the well completion. So casing and tubing data. A well consists of many casings. We only need the ones that where the flow is actually happening. So all intermediate casings and the surface casing and these things aren't important for BHP. It's only the production casing and the tubing that matters. And we need to know the inner diameter of the production casing and the production and the tubing, and the outer diameter of the tubing if we're going to do annular flow. We need to know where the tubing is, where the end of the tubing is, and to some extent we also need to know the pipe roughness. It's more of a second order kind of effect on the calculations, but it's one of the inputs to pressure loss calculations. So that's the input, the BHP calculations. So the BHP calculations, they rely on using single phase flow equations in pipe for pipe flow to model a multi-phase flow problem. That's what we're doing. And the way that's typically done is that we have a system looking something like this, where the water and the oil are flowing approximately with the same velocity. So we just lump them together by sort of how much of each there are in terms of rate. But the gas and liquid, they can flow with very different velocity. Gas tend to flow much faster. So there we have to use a correlation to make that final, call it single phase mixture, that we apply to the single phase equations. And that averaging, going from a gas liquid system to this single phase system, that's dependent on a correlation. I'll get back to why that depends on the correlation and why this doesn't. But the key is that there's a difference in velocity between gas and liquid, but less so between oil and water. That's why. Pressure gradient can look a bit nasty. It's a non-linear differential equation. We have three terms. We have the gravity term, and that's caused by the weight of the fluids, and it only acts in the direction of gravity. So when the well flattens out into the horizontal section, this term here becomes 0. Second term is friction. It works equally along the entire part of the well and is dependent on velocity. You see this V and the diameter. Those are the two numbers that matters most for the friction loss. And finally, we have acceleration, which is caused by rapid expansion of fluids, so gas typically, and it's only relevant at low pressures near the wellhead. If you have low pressures, then gas can become so very volatile or expand very rapidly for short distances along the well, and you can have pressure losses due to that expansion. It's referred to acceleration. Temperature is approximated by this equation here. You can combine some thermodynamic relationships to show that this differential equation for pipe flow makes sense. And what we do is that we assume that the temperature in the rock itself from surface to reservoir follows a straight line. So at the surface, it's the surface temperature. In this case, it's 60 Fahrenheit. And at the reservoir, it's the reservoir temperature, same as the fluid itself. Then the blue line represents the temperature loss in the well, which we also need to know the outlet temperature, the wellhead temperature. And then the profile is expressed by this differential equation. And what this differential equation primarily models is just the loss of heat out from the well to its surroundings. That's what this T minus T rock means. So that was sort of the single phase fundamental of it all. Now comes the multi-phase flow. So multi-phase flow, in terms of the bottom pressure calculations, what we're doing here boils down to whether we account for slip or we don't account for slip. And slip, let's start with the no slip first. So no slip assumes that gas and liquid flows with the same velocity. If that is true, we can define what is called a liquid flux fraction, sometimes a no slip holdup, and we can average the liquid properties, the liquid density and liquid viscosity, and gas viscosity and gas density by just by that liquid flux fraction. And this is a number always between 0 and 1, right? If we account for slip, by that meaning accounting for the fact that the gas has a higher velocity than the liquid, then we define something that's called a liquid holdup, or sometimes, which is 1 minus what sometimes is referred to as the void fraction. And that's defined a little bit differently. It's defined as the area of the cross-sectional area occupied by the liquid phase divided by the total cross-sectional area of the pipe. So liquid plus gas. And you can show that by flipping a little bit around, you can show that as long as the gas velocity is greater than the liquid velocity, then liquid holdup is always greater than the liquid flux fraction. And the gas and liquid properties are averaged by this liquid holdup instead of CL. And we denote those symbols typically with an S for slip. And the effect of using liquid holdup versus the liquid flux fraction is that the liquid holdup, if we don't account for slip and we use this one, then what we're doing is we're including more gas in the cross-sectional area than what's actually there. And it'll make the fluid property, this single phase mixture that we're creating, it will make that mixture too light. We're weighing the gas properties too much. So that's why we typically refer to it as a liquid holdup. It has something to do with the fact that how much of the liquid is left behind relative to the gas. That's one way of seeing it. But when we account for liquid holdup, what we're essentially doing is we're accounting for a smaller volume of gas or area of gas in the cross-sectional area, making the column of fluid at that point a little bit heavier. One thing I'm not going to talk too much about, but it's nice to know. In multiphase flow, there's often talk about flow regimes. This is one map showing that. There are many of them out there. This is by Gould et al. It typically shows up in petroleum engineering in pipe flow. And what they're plotting here is a dimensionless number representing a gas velocity or a superficial gas velocity versus a dimensionless number representing the liquid velocity. So you can think of this as gas velocity, and this is liquid velocity. And if you have a low gas velocity and a high liquid velocity, we're in the liquid phase is assumed continuous, and there's like a bubble flow regime. So we have a liquid filling up the well, and we have gas percolating as bubbles up through that liquid column. In the middle, that's where we start to transition from a sort of a continuous liquid phase to a continuous gas phase. That's when we can have slug flow. There's a transition zone, and going more into the high gas velocity. That's when the gas phase is continuous, and liquid is sort of carried as small droplets together with the liquid, or sorry, the gas. And also there will oftentimes be a liquid sort of adhering to the pipe wall, which increases the frictional loss in the pipe. That's what the gray correlation, for example, accounts for. So the pressure gradient can be rewritten a little bit. I don't know if you noticed it, but the previous equation had some sort of implicit that this acceleration term depends on the pressure gradient itself. But if we want to solve pressure gradient explicitly, then we approximate that velocity gradient as such, and we can arrive at this final equation. This here is the gravity term. This is the friction term. And this the denominator here represents sort of a correction for acceleration. And this equation will be used for all the correlations as a basis. The only thing that correlations what differs between the correlations are how they compute some of these properties, the averaging of them, essentially. So to understand a little bit all of these equations and what they all express, I'm going to go through a couple of, just plot a couple of key things like pressures and liquid holdups in the well for three different fluids. A black oil is sort of a liquid-rich well, a sort of mix of liquid and oil, or liquid and gas, sorry, and a gas-rich well. The well has the same configuration for all three fluids. Same well deviation survey, same casing and tubing. And there's no artificial lift in this case, just to make it simple. And first we can look at the pressure. So what are we looking at here? So for the two liquid-like phases, I've used Hagedorn and Brown to compute the pressure. And for the gas condensate, I've used gray. And the red line represents the case where we don't account for slip, where we assume the gas and liquid flows with the same velocity, using this CL to approximate the liquids. And you can see that there is a difference in all cases, actually, even the one that's fairly liquid-rich or gas-rich. You can see that there's quite a significant difference between the two, between accounting for liquid holdup and not accounting for liquid holdup. And the consequence in all cases is that if we use the liquid flux fraction, we're including too much gas in the cross-sectional area. And the result is we predict a lower bottom-hole pressure. We're predicting a lower pressure at all points in the well, but the bottom-hole pressure at the end here, that's what matters. And yeah, just to explain, so down to 7,000 feet, there's a tubing, 2 7/8-inch tubing, and the remaining 1,000 feet or so is a 5.5-inch casing, production casing. And at our about 8,000 feet, we have the top perforation. Looking at the liquid holdup, so these profiles can be a bit strange, and that has to do with how the correlations are predicting the liquid holdup and what the correlations are relying on. I'll get back to the details of the correlations, but it might look a little bit strange that it has some sort of discontinuous behavior in the liquid holdup. At the tubing, it makes sense. You're reducing the size of the tubing, or the size of the conduit that you're flowing, the pipe you're flowing through becomes narrower. A narrower tubing increases the velocity. And if we're increasing the velocity of essentially the gas, then we're carrying more liquid with us. So the liquid holdup goes down. So you can see in the larger diameter tubing, there's a higher liquid holdup than there is in the tubing part of the well. And actually in the gray correlation, you can see, in this case, the liquid holdup is fairly small, sort of at every point in the well, but the difference between the production casing and the tubing is quite significant. And that's just because the gas flows much faster in the tubing than in the production casing. Over here, you see something interesting, that the Hagler and Brown actually predicts a liquid holdup that is less than the liquid flux fraction. But that we don't allow. We always say that the liquid holdup has to be greater than the liquid flux fraction. It can't be less. And that's just because if it were less, we would assume that the liquid flows faster than the gas, which physically doesn't make sense. So we're always constraining it to that. And then it's just the correlation that has some inherent weaknesses. It can end up like this. So it's always greater than or equal to the no-slip holdup, or this liquid flux fraction, CL. So maybe what's more interesting is to sort of have an idea of what matters the most for which kind of fluid and where in the well. So what I'm plotting here is the three different sources of pressure loss, so acceleration, gravity, friction, as a percentage of the total loss at that point in the well. So the blue line is gravity, the red is friction, and the green one is acceleration. And as I said, the acceleration, in this case, the wellhead pressure, I think for all cases, is 200 psi. And that's just not low enough for acceleration to really matter. You need to be at 100 psi or less maybe for that to really start. You see slight curvature here, but not much. But it sort of behaves the way we would expect. In a liquid-rich well, the velocities are only not really that large and not really changing that much up the well. So gravity makes up for most of the pressure loss along the entire well. And in the tubing, there's a little bit of gas. It's a narrower pipe, so friction matters more. Going into the production casing, the friction almost goes to zero. And then because the well is flattening out here, essentially driving gravity towards zero again, it comes down a little bit. For a volatile oil, where there's a lot of gas, both free and in solution in the oil, that will come out of solution as the pressure goes down in the well. You see that gravity at the bottom or at the end of the tubing makes up for the most, but it switches as we get approach to the wellhead. And friction takes up more and more. And that just reflects that there's more and more free gas in the well, and that free gas is expanding very rapidly, and it's flowing faster and faster as the density goes down. There's more and more buoyancy difference between the two phases, and that drives the friction term. For the gas-rich well, friction dominates essentially everywhere in the tubing, but interestingly enough, it flips in the production casing. So even though in this case there is mostly a gas, it still flips just by changing the tubing changing the pipe diameter, the inner pipe diameter, from a 2 7/8" tubing to a 5.5" casing. So when you think of it, it sort of makes sense, right? And then in liquid-rich wells, gravity dominates. In gas-rich wells, or at least with some gas rate, that is, friction matters the most. So the correlations. So here you can talk in sort of great detail about it, or we can sort of brief. I'm gonna just lay out essentially what they do and nothing more, and then the rest is sort of left for you to study if you're interested. We'll just start by saying that there's one common equation, and that's the equation I showed you just now. And what differs is how these correlations compute the density in the gravity term, the friction factor in the friction term, the density in the friction term, and the density in the acceleration term. That's what really matters. And then viscosity, you saw, also is weighted by liquid hold-up. That comes into this multi-phase friction factor in the Reynolds number. But the densities are what matters the most. And these densities for the different terms are computed, may not be the same, and they may not be computed the same way for the different correlations. So the Hagedorn and Brown is from 1965. The liquid hold-up there is essentially calculated by 4 dimensionless numbers, defined as such. You take those 4 numbers, and then you walk a path through a couple of plots. So you have to graphically read off the corresponding value. So first you start with this n mu, the viscosity number, and you read off a number. And then you bring that number together with a couple of these other ones in here, and you read up the liquid hold-up divided by a sort of a correction term. And then finally you compute that correction term, and then you get the resulting liquid hold-up. And the pressure gradient in this case is calculated by setting the gravity and acceleration densities equal to that slip density. So that's just liquid hold-up times the liquid density, and then plus 1 minus the liquid hold-up times the gas density. The friction density is 2 times the rho m. That's the sort of the no slip density. So we use CL instead of HL to compute the density. So it's that square divided by the liquid hold-up. And the friction factor is computed by, as a function of the Reynolds number. So you use a Moody chart, essentially, where this Reynolds number is computed by geometrically averaging the viscosities with the liquid hold-up. That's a bit special for Hagedorn and Brown. One thing that came about later, but is very common to see for Hagedorn and Brown, is the so-called Griffith modification for to account for bubble flow. So Hagedorn and Brown is meant for liquid-rich wells, but it was figured out that for in sort of the onset of bubbles coming out of solution, when you go from a pure liquid column to early development of bubbles in the column, that the Hagedorn and Brown correlation was inaccurate. That's where this Griffith correction or modification came about. And what they essentially do is that they have a condition that they say, well, if 1 minus the CL is less than the maximum of this equation here, or 0.13, then we have bubble flow. So that's just a kind of a flow regime line, if you will. And if that's the case, we compute the liquid holdup in this case, where we just say that the slip velocity, the difference between gas and oil, is 0.8 feet per second, just hard-coded. And then this calculation here is actually from the definition of liquid holdup and the liquid and gas velocities. And there's also a slight difference to how the numbers are calculated. It's the same for the gravity and acceleration densities. But for the friction term, we're now assuming that, well, this is a primarily liquid with just small bubbles starting to coming out of solution. But it's primarily liquid, so we're just going to use the liquid density. We're going to use the liquid velocity and not the mixture velocity. And the Reynolds number is computed only with liquid properties to compute the friction factor. And what this results in is the plot I showed you, where you were following where liquid holdup was on top of the no slip holdup, and then all of a sudden it broke off. Just it's this Griffith modification that kicks in. Okay, so Beggs and Brills, and that's probably of the 4 correlations that we have in Whitson Plus, this is the most, call it, complicated one. It relies on different flow regimes, and it has different ways of computing liquid holdup depending on which flow regime you're in. And it also corrects the liquid holdup for the pipe inclination. The other correlations, they assume a vertical well, even though that's not always the case. That's the assumption. And the way it does that is that it first computes a liquid holdup for a horizontal well, and then they correct it for any angle from horizontal to vertical by this psi factor. And they are a factor of the flow regime. The no-slip, or sorry, no, not the no-slip, but the horizontal liquid holdup is computed by this equation here. And this correction for inclination is computed by this sort of nasty equation here. And the different parameters, A, alpha, beta, D, delta, and so forth, they are all dependent on which kind of flow regime you're at. And the different flow regimes have their different equations to determine which flow regime you're in. And they provide sort of a chart for that. It's on the next slide here. The original publication gave out this here. So you take that no-slip, this liquid flux fraction, you plot it against what is called the Froude number. And depending on where you land, you have either distributed, intermittent, or segregated. They later revised their flow regime into this map here. That's what's used today. You can see it similar, but not quite. And there's also now a transition zone between segregated and intermittent. And what you're doing there is that you're computing if you land in a transition zone, you're weighing intermittent and segregated just linearly with, I think it's a Froude number, if I remember correctly. And finally, they also have a solution for the friction factor, which is also corrected with this S. And that S is a function of the liquid holdup corrected for inclination. And finally, you can compute the pressure gradient by setting gravity and acceleration equal to the slip density and the friction equal to the mixture density. And the friction factor is computed with the Reynolds number using M, or mixture properties. And what mixture means is just we're using this liquid flux fraction to average the properties, linearly average properties. That's the difference between S and M. I probably didn't say that. Okay, so the last correlation is, not the last, but the third correlation is gray. It was published in a user manual for, I guess this is a surface controlled subsurface valve or something like that. It assumes a gas well with sort of mist, liquid in more like a mist form. So a mist flow regime is where the gray is supposed to work the best. And it corrects, primarily it has one way of computing the liquid holdup in such a regime, but it also has a way of computing or correcting the friction factor for this liquid film that's typically created along the wall. The liquid droplets are sort of adhering to the pipe wall, and that increases the roughness of the pipe wall, which again increases the friction. So that's what they do. So they have a way of computing. I'm not showing the equation of how they compute the liquid holdup. It's one equation essentially. And then they set the gravity and acceleration. Typically that's what's always done. Gravity and acceleration are equal to the slip. The friction is equal to the mixture. And then what's special here is that the Reynolds number, one of the inputs I'm not showing here, but another input to the friction movie diagram is this pipe roughness divided by the diameter, this sort of relative roughness. And in that case, they have a way of computing an effective roughness instead of the actual pipe roughness that you provide. And you have this effective relative roughness that will increase the friction factor. Finally, the fourth correlation is a newer one, Volta-Samayan-Gaillard. That's more of a theoretical one. It's just based on a review on a lot of correlations that are out there. There are many, many more than we support in Whitson Plus. And what they're just plotting here, so here they're plotting void fractions. So that's just 1 minus liquid holdup. But you can see they're plotting measured versus calculated for horizontal wells, inclined wells, vertical wells, all the data that they can find, and it does fairly okay. And there's so many different fluid systems here, and many different conditions involved or behind every point here. And the assumption there is that all the densities are just equal to the slip density, and friction factor is computed by this Reynolds number definition. Okay, so now that we're sort of done with the nasty equations, now we're going to go more into the flow paths and the different ways you can model bottom pressures and pressure loss in the pipe. And by flow path, we mean which way up the well does the fluids go, essentially. In Whitson Plus, you have a suite of different flow paths to select. You have casing, tubing, annulus, tubing and annulus, measured gauge pressures, and unknown as such. So we're going to start with casing. So there's two ways. So many of these flow paths, they have two ways of computing. You can either do casing without a gauge, then there's no tubing. We assume there's no tubing in the well, or flowing from the top perforation up to the wellhead and just a production casing. But if there is a gauge in the well, then you have the option of computing not from the wellhead, but starting at the gauge instead. And that reduces the length, both vertically and total, the whole length of the well. It reduces the length that we have to calculate using these multiphase flow correlations, and it consequently reduces the uncertainty provided by the correlations themselves. It does not remove the uncertainty in the rates and these things that you provide. If they're allocated, they obviously have certainties to them, but it removes, you'll see that if you do this kind of calculation, the correlations will be more or less on top of each other, a little bit dependent on where that gauge is placed relative to the top perforation. The same thing for tubing, only now we have a tubing in place and we're flowing up that tubing. The annulus is now just a static column of some fluid. And you also there have the option of either flowing with a gauge. Annulus sort of speaks for itself. It also has the same, but in that case, instead of flowing up the tubing, we're flowing up the annular space, or up the annulus instead. And there you can also either do from wellhead to top perforation or from gauge to top perforation. Tubing and annulus, or sometimes called parallel flow, that's a bit special. So then in that case, we're flowing up both the tubing and the annulus. And in that case, first off, we have to have very similar pressures at the casing head and tubing end, essentially the same back pressure for both, call it conduits. And the way that's done is that for every computation we do, we have to solve at the end of the tubing how much of the fluid goes up the tubing and how much goes up the annulus. The way that's done is that we compute the pressure down the annulus for a given split factor. We compute the pressure, we always compute from top and down. We compute from using the casing head pressure, we go down the annulus, and tubing head pressure, we go down the tubing. And then we see, are the pressures equal at the end of the tubing? If they're not, we have to change the split and try again. That's how it's solved until we find some point where this matches. And finally, measured BHP, that used to be, so some things have changed here since last time. So measured BHP now, if you select that, what it does is it merely echoes the gauge pressures that you have provided. No calculation is made here. It's just giving back what you specify in the production data as the PWF for the bottom hole pressure. And then what's new since last time, I guess, is the unknown. So in some cases, it might not be clear. Let's say you've just acquired an asset and you're not entirely sure about how these wells are operated and how they are completed, etc. Then we have a logic in place for this unknown flow path, where it's such that if the casing pressure is greater than the tubing pressure, then we assume the flow goes up the tubing. So we're just using like the smallest back pressure. That's the path of the least resistance, and that's where we go. So if the casing pressure is greater than the tubing pressure, tubing head and casing head pressures, then we go up the tubing. If the opposite is true, then we go up the annulus. And obviously this assumes that there is a tubing in place. If there's not a tubing in place, and we just go up the casing. There's no real choice. It's just casing flow. Okay, so that was the flow paths, and this may be going through a bit of a fast pace. We'll touch upon all these in the exercises later on, and you have the material to skip through whenever you like. Now we're going to go into the artificial lift methods. The first one there is gas lift, and there's 3 kinds of gas lifts that you can specify. You have what is called pour buoy, which is essentially just injecting all the gas at the end of the tubing. We have valves. You can specify a set of valves along the tubing string with depth and with corresponding closing pressures for each of them that we can use to decide at which valve is the injected lift gas going into the tubing and then up again with the wall stream. And then finally, there's also new since last time is automatic, which basically solves down tubing and annulus and finds where the pressures are equal, and that's where we assume the gas is injected. So, pour buoy, if we have selected tubing flow path tubing, and then gas lift and pour buoy, then we inject gas down the annulus, down to the end of the tubing, and then the lift gas together with the wall stream goes back up the tubing. If we have annulus or reversed gas lift, that's the flow path annulus, then the opposite. We do the opposite. We inject the lift gas down the tubing and we flow together with the wall stream up the annulus. With valves, you can specify any number of valves, typically anywhere between 1 and 15 maybe, with depth along the tubing string. And each of them will have a closing pressure measured at the surface. And that typically decreases with depth. And what we say is that when we start at the top, we test each valve and we say, okay, is the casing pressure at the casing head pressure at this given day greater than the closing pressure for valve number I? If that's true, we inject the gas there. If not, we go to the next well and we test, is it greater here? Yes, okay, then we inject there, so forth. That's the case when we have tubing. When we have annulus, reversed gas lift, there's only 2 things that can really happen. Either there's an option of always having the last valve open, so there's no opening or closing pressure. It's always open. In that case, when we do reversed gas lift, the lift gas is injected through that last valve. If that's not ticked, this option, then we do pour buoy. So the gas is injected into the tubing, goes down around the tubing end and up the annulus together with the lift, together with the wall stream. And finally, automatic, as I mentioned. So there we compute the pressure down the column. In both cases, both tubing and annulus, we compute the pressure down the gas, the red line. We compute the pressure, including the lift gas, obviously, down where the well stream is, all the way down to the end of the tubing, and we see if these lines cross anywhere. And at the intersection between these 2 lines, that's where we say that the lift gas is injected. If we're in a situation, for example, because of bad data or something like that, that these 2 lines does not intersect, we just assume that the lift gas is added at the end of the tubing. Okay, so the injection can happen anywhere along the well, but not deeper than the end of the tubing. And this here automatic valve or injection depth together with an unknown flow path can be very powerful if you know that there is some gas lift going on, but you're not entirely sure where the wells are or where the valves are and these things. And then this can be of great help. Okay, so rod pump is solved. It's a bit more complicated than gas lift. It's not just adding some gas into the well stream. Here we have to divide the well into 3 segments and calculate the pressure different ways in the 3 segments. The first segment is from the top perforation to the end of the tubing, where we assume the piston of the pump is. Then we just do regular multi-phase flow in a production casing. Then from the end of the tubing to a user-defined liquid level, we assume that there's some sort of stagnant column of liquid with gas moving slowly through it, but it's primarily liquid. And the third part, from the liquid level to the wellhead, it's single-phase gas flow. And recently we made a change to the rod pump based on some studies we did and also some feedback we got. The current method that we had in place was emphasizing the gas too much in that liquid stagnant or static liquid column. So what we've done now is we've implemented what you see here on the left. So we had a discussion internally and also some literature review. And what you can think of these four figures here is sort of like, here we have no gas, here we have a lot of gas, and then how does this situation change as we have more and more gas? And at some point, we don't know exactly where, there's going to be so much gas going through this liquid column that there won't be a liquid, well-defined liquid level anymore. The gas is actually going to drive the liquid with it up the annulus. That's what this part to the right here is showing, which is currently under development. What we have now is these situations here. So we have a hard-coded, for now, a liquid holdup of 0.7. So this column cannot be more than 30% gas in the cross-sectional area. And the way this is modeled is we're using an equation for like bubbles rising through static liquid. Sometimes referred to bubbles like these are referred to like a Dumitrescu or Taylor bubble to account or to calculate the liquid holdup. So they were assuming that the liquid velocity is 0 and the gas velocity is the bubble velocity, and then the slip velocity is also the bubble velocity, because there's always the gas minus the liquid. And there in the liquid holdup can be anything between 1 and that critical value. And then what's to come is to sort of quantify this critical liquid holdup. Instead of hard setting it to 0.7, we want a method of estimating that and also be able to compute the amount of gas and liquid going up the annulus if the gas is actually able to move the liquid with it. It's not stagnant anymore. At some point, this stagnant liquid bubbling gas is not valid anymore, and that's when we sort of flip from this side of the picture to that side of the picture. Okay, ESP we can also do. ESP in the sense that what we're really using the ESP for is just a gauge that it has, by meaning that there's always a gauge at the inlet of the ESP, which means that we can compute from that gauge down to the sand face instead of from the wellhead to the sand face or to the top perforation, again, to reduce the uncertainty in the correlations themselves. That's really what ESP is doing. We don't model the ESP itself and the pipe and the pressure drop in the tubing and the added pressure from the ESP. That would require quite a bit of technical knowledge about the ESP itself. And finally, plunger lift. It's not really something we model, but we can sort of come with a recommendation of how you can model it if you really will, if you really want to. You can treat it similarly as a rod pump, where you're sort of assuming that we're using some sort of average when the sort of the plunger is going up, essentially. But you might have to change the GOR manually to sort of get a better capture of it all. So I'm going to leave this slide more for a personal study. Okay, I think it's only tuning and just a slight tease of what's to come left. So I think I'm just going to go through that and then we take a break. About 6 minutes left till it's 4 o'clock here, 9 o'clock in Houston, I guess. So we're just going to press on. So tuning was also added last year, and it's new since last time this course was taught. And what tuning is essentially is that you can vary two parameters, one that affects the computed liquid holdup from any of the correlations, and one that affects the friction factor from the correlations to improve the call it the quality of the or predictiveness of the correlation. And you can do that by this sort of menu. There's a small button up at the right corner. We're also going to go through this in the exercises where You can tune one correlation at a time individually, and you can also show a fit of the few points that this routine samples of the entire production history and tries to match or improve the match of the correlation versus the measured pressure. An important thing to note with tuning, and is a question we've gotten a lot, and it's where it's maybe appealing and interesting to use tuning, but unfortunately you can't, and that's with ESPs. So ESPs often come with measured pressures, but you have to remember that measured pressure is at the inlet of the ESP. When you're doing tuning, you're computing the pressure from the wellhead down to the gauge. So what you would do then is that you're computing a pressure from the wellhead down to the outlet of the ESP, but you're not accounting for the delta pressure that the ESP itself is giving. So I can guarantee you will have a very hard time fitting the correlations to the measured pressure, because the correlations will have to account for that large increase in pressure that the ESP itself is giving. So just be careful. So just make a note of that and be careful that even though you have measured pressures from an ESP, you can't really use that without having knowledge about how much the delta P from the ESP itself is.
Yeah, just a question here about the tuning factors. We have two tuning factors.
Yeah.
Which one to use, or should we use both? I guess just like the mechanics of it is when we tune both of the parameters at the same time, and they're by default like one, and they can change up and down, I guess, depending on the changes that's needed for that particular case. But do you have any other things to add to that, or which of these tuning factors that can be more important than another?
Yeah, so I think a little bit reflects what I talked about earlier, right? What really matters in for different fluid systems. So we saw that for gas rich well streams, friction matters the most. So you can expect that this friction factor tuning parameter has a larger impact than the liquid holdup parameter. But generally speaking, I would say that the alpha, or the liquid holdup correction, will have a larger impact. You can make, there are smaller variations in that, will have a larger impact on the correlation than the friction factor correction does. That will be typically in all cases. And the reason for that is because these unconventional wells, they don't have a lot of throughput. So what we're really tuning here is mostly the gravity, or sort of the, essentially how much liquid or gas do we want to weigh into the gradient. And the liquid holdup correction is going to affect that. And yeah, I didn't mention that, but it's like Matthias says, these are one by default. So these are multipliers. So if they're one, you're multiplying with one, you don't do anything. And if they're different from one, you're doing something with the liquid holdup. And the details of this you can find in the manual. I'll give you a reference for it a few slides down, but that's really how it works in a nutshell. But when you click tune, it tunes both of them. So it tries to find the best combination of two parameters. And you can also change these manually. You can type whatever number you want and hit save, and it'll use that on the correlations instead of the default correlations.
Stian, just a couple of relevant comments or questions here related to this that we usually get, so I thought it might make sense to clarify here. So first, kind of what's the justification for going and doing some tuning on this? Is this like, why don't you trust the correlation as is? That's the first thing that a lot of people kind of would like to know. And the other thing is, if you went and did this for more than one well, how you go about it, doing it for more than one well, and how you apply that to wells where you don't have gauge data, for example.
Yeah. So I guess those two questions sort of ask a little bit the same thing, but the reason so these correlations are, sometimes they are actually very good. You can see in some cases that if you have good measured data of the rates, and you also have a gauge that for essentially for liquid rich oil, Hagedorn and Brown is often very good without tuning at all. but it can be better, and that goes for the other correlations also. And let's say if you have a pad with I don't know, 10, 15 wells that are completed the same, they produce from the same area, they have much the same properties, same kind of well stream, and you only have gauged in say 1 or 2 of them, then one thing to do would be to tune the correlations to one of the wells and then apply those tuning parameters to all the other wells similarly, and then you can sort of assume that you're doing a better job at predicting the BHP in the wells where you don't have a gauge. That will be the main use case, I think, for tuning as such. But you can see in many, or at least I've seen in many cases, that the correlations themselves are not that bad. And there's also one here, I'm just going to mention that now. There's also one thing here you can also use to tune. It's not really a tuning, but it's more like shifting, and that's if you, in the early periods of the well, when you're above the saturation pressure, essentially anywhere in the well, it's a single phase liquid. If you see that you're not really matching the gauge pressure, one thing to try then is to, for example, change the salinity of the water. It's always be 0 by default. But increasing the salinity makes the water heavier, and that can help increase the BHP up towards the gauge. So typically in the single phase period, when it's liquid, then it's just a matter of densities being accurate or inaccurate. And the gas and oil densities are given by the fluid definition. And then the water density you can change by changing the water salinity. Does that answer your question, Mo, or did you think of?
Yeah, that's very good. Yeah.
Okay, great. Any more questions in the chat? No, good. Yeah, so references, we have 2 sources of information for all this pipe flow material. You can go to the wiki, wiki.whitson.com. There are a couple of slides or a couple of pages there, one on like well pressure calculations in general and one for each correlation. And obviously also for the BHP calculations in Whitson Plus, you can go and read in the Whitson Plus manual for BHP calculations. And it'll explain a lot of these different things that may be unclear. And it also has some nice GIFs, like explaining how you put in data and these things. Okay, so to come in BHP, 2 things are in the making right now, actually. It will be hopefully out with the next release in mid to late June. The one is called, what is called so-called the quiet side or the silent side, or it has sort of many names. But the point is simply that instead of using the multi-phase flow correlations down the flowing part, when you have a tubing installed, why not go down the static column in the annular space instead? And but then obviously you have to make an assumption of what that annulus is filled with. To begin with, that's going to be assumed that it's purely gas, just because it's very hard to know exactly where, if there's more than one phase there, if it's gas, oil, and water, for example, or some combination of that, we don't really know where that transition is. But going down a single phase column will be generally much more accurate than using the correlations down a flowing multi-phase fluid well stream. And then you would do the calculations in 2. So from wellhead down to the end of the tubing, you would go down that sort of static gas column. And from the end of the tubing to the top perforation, you do regular gas flow. But then all the correlations will have the same pressure down to this point. So the uncertainty and the correlations themselves will only be reflected by the last point. And the closer the tubing is to the top perforation, hopefully the more accurate this prediction is. Obviously, assuming that the gas can be assumed filled with one fluid gas. For gas lift, this is actually quite useful. In that case, we know there's only gas in the annulus, and generally it will be very accurate to compute the pressure down the annulus, or if it's reversed, down the tubing, but in the gas column down to the injection point. And then if we assume that there's little to no pressure drop through the valve itself, that it's not acting as a choke, but it's more just flowing freely through, then you can, from that injection point or down to that injection point, you compute in a single phase gas column, flowing gas, and then for the rest of the way you do multi-phase flow, and that will hopefully reduce the range of pressures predicted by the different correlations and bring you closer to what the value should be. Second thing in the making is vertical lift performance tables, VLP tables, or sometimes just called tubing tables. They are primarily used to control numerical model on tubing head pressure, or to compute the tubing head pressure resulting from some predicted bottom hole pressure profile. And the way that's done is that you have to provide some sort of range of tubing head or wellhead pressures, GORs and water oil ratios. And then you compute a BHP for each of these combinations. And you're essentially creating a lookup table for the numerical model. So when it has some, if it was run on tubing head pressure, it just takes the current tubing head pressure, goes into the table, converts it to a BHP, and then that becomes a constraint. And if you're running it on a different control, it's more like a sort of solving for tubing head pressure, and it returns you the equivalent. But the gist of it is that you provide three properties as an input, and you get a BHP as the output from a lookup table. And that's it for the theory part. I hope most of you are still awake. If not, we'll take a break now for to let you guys get some refreshments and a cup of coffee maybe.
Yeah, let's be back in 14 minutes. So in Houston time, that will be 9:20. Just a recommendation for everyone about the exercises that we'll go through now. There'll be a little bit of manual entry of numbers, and they will of course be shared on Mo's screen when we go through the exercise. But it can be very helpful to also have the slide deck somewhere readily available for you if you have two computers available on your laptop or in your office, that you can have that slide deck with the exercise, because you need to type in some of those numbers. It's not a lot, but it's a little bit. So when Mo is flipping back and forth between the software and the slides, it can be really helpful to also have that next to it. So just make sure you have the slides in the exercise part just readily available for you. And we'll be back here in 13 minutes. And thanks, Dan. Great work.
Yeah, no problem.
Yeah, I think we're ready again, Mo. Just continue with the exercise piece. We're not in a rush or anything, so we can just take our time on the exercise. It's most important for people to get familiar with all the different flow paths and whatnot. That can be a little bit overwhelming, and the same thing for, of course, the artificial lift stuff. So I'll leave the word to you.
All right, thank you very much. Hello, everyone. So my name is Mohammed Dahouk. Everyone calls me Mo, and I think from the names, I see that I've probably interacted with most of you. But those that I haven't interacted with, hello and nice to meet you. I'll be going through the exercise piece of this course, and the agenda for the exercise will be basically we'll be covering the key features and the key functionality that you have within the BHP calculation in Whitson Plus. And that is calculating bottom hole pressures when your well is in gas lift, for example. And within the gas lift, as Stian talked about, there's 3 different configurations that we support. That's the poor boy configuration, having the valves specified versus depth, or also the automatic configuration. And we're going to go in detail how to do that in the software, how to enter the data for those types of configurations. And we're going to go through a rod pump example, also an example of a well with ESP, and also some new functionality that we have implemented that is related to the calculation settings, how you can adjust those settings and what that means to you. Before we jump into the a part that kind of sits on the side of the BHP, but it's very important, and a lot of people have been using it since it was released, and that's the BHP tuning. So we're going to go through the exercise of how you do the tuning, what is important, and how you change things in the tuning exercise as well. Okay, and in the end, we're going to cover quickly how to do the BHP calculations using the mass upload sheet. So how do you upload all the data needed to do bottom hole pressure calculations using mass upload? So you don't have to input it one by one, okay, well by well. But important that we go through it well by well first, so you understand how it works, and then you can just go ahead and use the mass upload sheet for your convenience. So for going through the exercises, I don't know if you see the top here. Let me see. Yeah, for going through the exercises, what we're going to be using is our software Whitson Plus, and the domain is here, courses.whitson.com. It's also the domain that I have sent in the chat a couple of times now, just for everyone to access. Very important. This is not the same as your company domain. So if you're with Marathon, and it's not marathon.whitson.com, it's not ovintiv.whitson.com, it's courses.whitson.com. So you need to go to that is specifically for the course, and the username is going to be your email address, and the password is WhitsonBHP 2023. Just look at the capitalization here. If you're not able to access this, then just send an email to Matthias or to support@whitson.com, or write in the chat here that you're not able to access, and let us know. So I'll show you how that is done right now. So I'll go into my web browser. I'll just log out here to show you how you should do it. So I'll just go into your web browser. You're going to type the URL, which is courses.whitson.com, and then you're going to go there, and then it's going to ask you for a username and the password. Your username is going to be your email address, and the password is the password that I showed in the screen just a second ago. It's WhitsonBHP 2023. So you type those, and then you log in to the software, and once you come in, you'll be brought directly to the field overview. And if you had more than one field, probably in your own company software, you have more than one field. So in this case, for the course, we've only uploaded one field, which is the Permian field. And if you go into that, you should be able to see, if you click onto that field, I'll just do it again, click on the field, you should be able to see a project. I have a long list of projects because I can see all the projects that are there. But in your case, you'll see only the projects that correspond to you. So you should see a project with your email name, and the owner of that project is you, and the project is private. What that means is that the project is being private. It means that only you can see it, and I can see it from my end because I'm like the super admin here on the end. I have the support email. but otherwise no one else within the domain, within your company, no one else will be able to see this project. Okay, so everyone that has gotten access to courses.whitson.com right now, please double check that you have also a project with your email address within the field. So you go into the field and you should see a project with your email address. If you're Andy, if you're Anna, Amy, etc., you should find a single project with your email address in it. Okay. I'll go to my project now here. You can search. If you had multiple projects, you would be able to search the projects here. So if I type Mo here, you see I have a couple of projects on that are named Mo. But this is what you should be able to see inside your project. Okay. So you'll be inside the Permian field, and the project name will be the project, your email address. And inside there, you'll find a couple of wells. You'll find 4 wells that correspond to the different parts of the exercise. Okay, so first you're going to have the gas lift well, rod pump well, the ESP well, and the BHP correlation tuning part. Okay, I'll just give 30 seconds for everyone to make sure that you got here. And if there's anyone that doesn't have access to the software, anyone that doesn't see the wells, please shout out, send an email to Matthias, or just write it in the chat. Okay, I think it looks like people have gotten in. Yeah, so we'll start with the first well, and this is basically, we're gonna be calculating bottom hole pressures for a well that is on gas lift, and the gas lift configuration is a pour buoy configuration. For that well, so we have production data that is already uploaded for us, and that production data also includes not only oil, gas, water rates and surface pressures, but it also includes the gas lift rate. So to go to that well, from within your project here, you're going to click on the gas lift well, the first one there. So now you'll see that the software at the top, in this navigation bar that you have at the top, it's going to tell you, like, it always tells you where you are, like your coordinates at that point. Right now you are in the field that's named Permian. The project should be named your email address, and the well is the gas lift well. And the analysis is a layer under the well that you can have multiple analysis for the same well, and you should just be in the main analysis. Okay, so for the gas lift well, we're gonna just go into the production data here on the left. You can either click here, production data on the navigation panel on the left, or you can click on the production data here. Either way, it will take you to the exact same place. That will take you to the production data. So as I said, we have oil, gas, water rates. We have pressures, tubing pressure and casing pressure. And we also have gas lift rates. If you want to isolate, one of the series in any plot in Whitson Plus, you just go to that series. For example, I want to isolate the gas lift here. I just hover over this and double click on it. And then it will isolate that series. It will be only that series that's going to be shown on the plot. So now I see here my gas lift rate versus time for this one. Okay. If you double click again, then it brings everything back. And if you single click on any of them, then it removes them. It toggles on and off the series. Okay. That's just a reminder for many of you. This will be like very repetitive, but we have to remember that we need to cater for the wide audience that we have. Okay, so the objective, what we are going to try to do here, as I said, is the course is focused on bottom hole pressure calculations. So what we want to do is go and calculate bottom hole pressures, and that we can do on this navigation panel on the left. We'll go to bottom hole pressure here. Okay, and we'll see that here we can basically calculate bottom hole pressures, but we're not going to do that yet. And this is something we see many people when they start using the software, they just jump here and start calculating bottom hole pressures. The reason we're not going to do that yet is because we need to make sure that we have the correct data for making this calculation. We have the correct inputs for making this calculation, okay? So the first input, like Stian had talked about in the theory part, the first is that we have the rates that we talked about in the production data. So we have the rates and we have the surface pressures. But then we also need to tell the software a little bit about how the well is made. We need to tell it about the deviation survey. And we need to also tell it what type of casing we have, what's the diameter of that casing, what type of tubing we have, and then we will select flow path and artificial lift method. So let us go ahead and start doing that. I'm going to switch over to the slides to provide you with the information for this well. So to start with, we're going to input the well deviation survey. It's not a lot of data, so it should be fairly straightforward to just copy or transcribe from the slides into the software. So we'll start with inputting the values that we see here, which is the well deviation survey. In general, what you're going to see is that your deviation survey is going to be a lot more points than this, and you can just copy paste from an Excel sheet that you have the deviation survey into the software. That's fairly straightforward, but in this case, we just wanted to make it simple, so we just made a very simplified version of the deviation survey. So just go into the software and input these values, basically 150, 150, 7600, 7515, and then the last point 18600 and 7220. So I'll go ahead and do that as well. So we have 150, 150. We go back here, 7600 and 7515. That's this, 7600 and 7515. And then if you need to add more rows, just click on the last row that you have and press enter.
Excuse me, I get an error when I put in 18400. It says value must be less than 12,000 feet.
When you put
18,400.
Yeah, that's because you've put the bottom perforation depth before you put the deviation survey. So it's just you just have to update the deviation survey, and it will not give you that error anymore. So what it's telling you, you've updated the bottom perforation depth, but the bottom perforation depth that you have given is you've given it that's larger than the deviation survey. So just update the deviation survey, and that will go. That's why we in the exercise we're doing actually first the bottom of the deviation survey, and then we update the depth. Okay, the perforated interval. Okay, so this, if you update the perforation depths before you have the deviation survey, then it will give you an error, and the error will look something like this. If I do here 18,400, the error will tell me that the value of the bottom perforation must be less than the largest value in my deviation survey. It's just like, it's checking that the deviation survey is consistent with the perforation depths that I'm providing. So that's because you haven't provided here. You do this, 18600 and 7220.
Got it. And how do you add more lines? Because I only had 3 lines.
Very good. So you click on the last line like this and press enter, and you can press enter as many times as you want. Did that work?
Yes, it did. Thank you.
Perfect. And actually, this might seem like, okay, entering and all that. In general, what you do is just, as I said, you copy paste from an Excel sheet. You might have like 500 inputs for the deviation survey, and you just come here, control V, and it pastes the whole thing here. So it's much less cumbersome than this, but it's just for the sake of the exercise to get familiarized with the kind of nitty-gritty details of the software. So once you've input the deviation survey here, you can click on this button here to view the plot of the well deviation survey. You see this button here? If you click on that here, it will show you the plot of that deviation survey. Okay. And then the next thing we're going to do is what Taron had already gotten ahead and done, is to update the perforated interval. So we're going to say that the top perforation in this case is at 7,600 feet. So I update that here. And the bottom perforation is 18,400 feet. Okay. Everyone is able to do this. Is there any questions or comments?
For some reason, the whenever you pull up that plot of the well deviation survey, it's not fading in or thickening the line where the perforations are.
Let's see. Yeah, that's a good point. Actually, it doesn't even show the perforated interval. I think yeah, it's probably because of the number of points.
It's because of the number of points, Mo. It would have shown if it was more points.
I think when you have more points, yeah, then it will show the deviation, the perforated interval as well.
Is there any problem putting in your whole survey, or do you recommend an abbreviated survey like this?
No, we recommend actually just put in your whole survey. The reason we didn't do it here is just to avoid like too much copy pasting, actually. And you'll see in the other examples, it's already uploaded with the full deviation survey. So that's what we would recommend to do. So you just go copy paste the entire survey here, and you'll find it very easy to just copy paste the whole thing. There's no limitation in that sense. Any other questions or comments? Okay, perfect. So one thing that we see also, a lot of people when they start using the software, at least, they input the deviation survey, and sometimes it's not very intuitive to see that you have to go to this second step, which also contains important data for the calculation. And many times we get like a support ticket or an issue like, hey, my bottom pressure doesn't look to be right. And it's generally because people have filled this first step where they put the correct well deviation survey, but they haven't added the well data. Okay, that's what we'll do here. So here, what we want to do is we want to provide the information related to the casing that we have and the tubing and the flow path and artificial lift. Okay, so I'll just flip back to the presentation here real quick, and we're gonna try to reproduce the wellbore configuration that we're seeing here. Okay, so what we have in the casing part, we have basically first casing that goes down to 7,500 feet. That's a 5.5 inch casing, and we have a second casing that is a 5-inch casing that goes down to basically the toe of the well. Okay, so we're gonna input these values in the software, and there's two ways to input this in the software, like the casing information and tubing information. There's two ways, and in general, I see that people either do one or the other, and sometimes don't realize that there is another way to do it. So we're going to go through the two ways. For the first row, what we're going to do, we're going to try to use this button here. And what that does is that it takes us to what we call the casing and tubing catalog. So we're going to try to do that here together. We're going to go, first we see that we have one casing only here, and we want to add one more, because in the wellbore configuration that we see here, it's two casings that we need to have, two casing strings. So the way we do that is that we click on this plus button here. That will add a new line for us. And for the first casing, okay, it's already the correct ID that we have. It's the correct internal diameter. We need to only adjust the bottom MD for that casing. So that would be 7549. We're going to put that here, 7549. Okay. And for the second casing, that's something that you can input here directly. For the second casing here, look here, this is basically a 5-inch casing. This is the internal diameter of a 5-inch casing. And if I go here, I could write that number directly. I could do 4.276, enter. That works. It's fine. And many people do this. I actually generally do this. But the other way to do it, if I delete this number from here, is to go into the catalog here. You click on this, you go into the catalog, and that will bring up the casing catalog for you. And here you're going to be able to find, okay, what type of casing do I have? I have a 5-inch casing. So you're going to find the 5-inch casing here. And then together with the weight of that casing, in this case, it's an 18 pound per foot, you're going to find which casing you want to select. And when you select it, it will populate it with the right ID and the right roughness, the right internal diameter and the right roughness for you. Okay. And then in addition to that, the catalog only has the diameter, right? It doesn't really know where the casing where the casing is landing, or where the top of the casing is. So that's something that we have to provide. So in this case, for this second casing string, the top is going to be at 0, so 0 here, and the bottom is going to be at 18,598. Okay. Now your casing data should look something like this. If not, then you need to update it. Remember, you can add the second casing string by clicking on this plus button. If you have 2 already, then you're good, and then you just have to update the values. Any questions?
Will the calculation change depending on that first casing string, since it's, I guess, covered by that second casing string that goes down to 18,598?
Yes, very good question. Yeah. So in this case, the calculation will not, it will not be affected by this first casing string, because it's fully covered by this second casing string. That's what you're saying, Mark, right? So basically,
Yes.
the second casing string is covering from the top to the toe of the well, and this is going to be the one affecting your calculations. Yes. Many people still have actually the complete. Here I only put 2 just for the sake of the example, but many people actually have the complete list of casing strings, just so you have a place where everything is documented. And also because many people connect this directly to a database like WellView or something along those lines, and then you have already that data populated there. So it's just a matter of passing it on to Whitson Plus. Good question, Mark.
Thank you.
Okay.
If you use a different top measured depth for the second string, then merge the 2 together.
Could you say that again? Sorry.
Yeah, if you do have a different measured depth starting at the bottom of the first string, then it'll merge the 2 together in the calculations.
Exactly right. Yes. Yeah. So you could have a top MD here that's starting, let's say, at 7,000, and then it will merge the 2 casing strings together. Does that make sense, Chris?
Thank you. Yes.
It's a very good question. Right. So so this is how the casing will look like, and you'll see. Actually, I think maybe I have an example later in the course where that's the case, Perry, where you have like a mixed casing here, but I'm not entirely sure. Okay. And then once we have the casing in place, then the next thing we have to do is to go ahead and update the tubing part. Okay. So for the tubing, we have to also provide the bottom depth, the bottom measured depth where the tubing basically is landed. And then we have to provide the inner diameter and the outer diameter of the tubing. The reason we don't need the outer diameter of the casing is because the reason we need it for the tubing is because that's used to calculate the annulus size between the tubing and the casing. While for the casing, we don't need that. Okay, so for the tubing, it's important to also provide the outer diameter because that's going to dictate the size of our annulus. And so in this case, it's basically 2 3/8 tubing that we have, and we're going to go ahead and either input it manually, like I said, just a reminder that you can do that. So you can do 1.995 here and 2.375 here, and then change also the depth. And I think the depth was 7.325. Or let's say you didn't have this, you only knew, okay, it's a 2 3/8 tubing. So you go into the catalog again, and you're gonna find the tubing size that you have. It's a 2 3/8, and then you also want to have the weight, which is gonna basically tell you what's your inner diameter. So 2 3/8 in this case, we know that the inner diameter was this, so that was the weight. Just go back there. Yeah, this is the one. Okay, you can pick it directly from the catalog or input the values. Okay. Everyone got here? Perfect. So so the next thing we're going to do now is, now we've input casing and tubing data. So now we've told basically the software how the deviation survey looks like, how the casing looks like, how the tubing looks like, and now we have to tell it how it's supposed to flow, the flow path and the artificial lift. Okay, so that's what we're going to do by just changing the flow path here. As you see, by default, the software will always default to unknown, because in the absence of a flow path, that's your best guess. It's gonna use the surface pressures to guess if it's flowing through tubing, through casing, or through annulus. And that's the kind of your best guess if you don't know. But if you know, like in this case, then you just adjust it. So in this case, it's we know that we're flowing through tubing, and we know that this well has artificial lift, as it has a gas lift. It's on gas lift. That's what we said, right? That's the whole point of the exercise. So the well is flowing through the tubing. Artificial lift is gas lift, and then on the gas lift configuration, it will select by default. The first one is poor boy, and like we discussed earlier, like Stian showed earlier, poor boy means that you're basically injecting. If you have flow path tubing and you have poor boy, it means basically you're injecting through the annulus, and then that gas is flowing at the end of the tubing into the tube. Okay, there's no packer, there's no valves in the system. All right, so your wellbore configuration should look something like this. Just make sure all the values look the same, and then click Save. In the software, when you click Save, the software will try to validate that you haven't made a mistake. So if you get like an error, like your red warning here saying something like your IDs are wrong or something like that, just let us know what error you're getting and we'll try to help you. But the software will validate that the values that you input made sense. For example, that the diameter of the tubing is not larger than the diameter of the casing, and that the depths make sense, etc., etc. Okay, so just click Save. Now you've saved the inputs. You've said, okay, now I have the production data has been input. Now I have the wellbore configuration, the deviation survey, and now we're ready to calculate bottom hole pressures. You can click on this button here to calculate bottom hole pressures. Now basically the software is going and calculating pressures versus time. For each point in production data, you have, for each point that I have data for each time step that for which I have surface rates and pressures, I'm able to calculate a bottom hole pressure. That's what I see here. Can anyone confirm that you got the results back from the calculation? And if anyone hasn't gotten them, please let us know. When you click calculate bottom hole pressures, you should see a plot like this popping up with the results. Can anyone confirm it's good?
Yeah, bunch of thumbs up here, Mo.
Okay, awesome. So one thing that a lot of people ask us about, and I think actually it's a little bit confusing sometimes for people, is that in general, what we're used to as engineers when we're doing bottom hole pressure calculations is that we specify to the engine that's doing the calculation, we tell it, I want to calculate with this correlation. I want to go and make the calculation with Hagedorn and Brown, for example, here. Okay. What's different in Whitson Plus, what we do a little bit different in Whitson Plus, is that we know that there's uncertainty associated to each and every one of these correlations, these multi-phase correlations. Okay. And what we like to do is, like, we don't want to ask you which one you want to calculate bottom hole pressures with. We want to show you how the bottom hole pressure calculation will look like for every single one of those correlations. So we want to tell you, hey, here's how it would look like if you did it with Beggs and Brill. Here's how it would look like if you did it with Gray. And then we want to empower you as the engineer to make the decision based on this plot that you see in front of you, to say that you want to pick one of those to be used in further engineering calculations. And that means for your flowing material balance, for your analytical RTA, for your numerical model, for your nodal analysis, for every single engineering calculation that you do, now you have to make a decision and you're going to say, I want to use Hagedorn and Brown. But that decision that you made it informed based on this plot, based on the spread that you saw on this plot, and you said, I like this. I know that I'm going for the minimum one, but this is the one that I'm going to use. It's the Hagedorn and Brown. And if you went for Beggs and Brill, you pick Beggs and Brill, that's fine as well. But then you know that you're picking the one that's giving you the highest pressure. Okay, that's just something that we like to do. So many times what people think is that when you change here, which one you select, you need to rerun. And that's not the case. The calculation has been run already for all the correlations. And all you have to do here is select which one is the one that you like, which one is the one that you would like to use for this particular case. Okay.
Can you show one more time how you highlight just one curve on the graph?
Awesome. Yeah, you do that. So if you have all the curves in the graph like this, you want to highlight only one, you go and hover over the series that you want. Let's say I want to have the Hagedorn and Brown. Double click on that, then it will highlight, it will isolate that one. And if you double click again on that one, then it will bring everything back.
Okay, thank you.
And then you can also single click on any of them to remove them individually. So if you wanted to remove only one or a couple, then you can just do that as well. Okay. Any other questions or comments? Okay.
Why is the measured bottom hole pressure higher than all of the correlations for this well?
Yeah. So this is just it's part of the exercise. You'll see later on. We're gonna do some tuning, and so it's just part of the exercise. This actually the measured pressure here is just another calculated. It's not actually measured. Okay. So that's it's part of the exercise. Did that answer your question?
Yes, thank you.
Okay. Any other questions? Good. So now we're going to go and try another configuration, and that's we're going to go and try the gas lift configuration, but where you input actually the valve depth. And that you can do basically by changing only the gas lift configuration from the well that we have. And once you have changed that, then you're going to get a small edit icon next to it. You can just click on that edit icon, and it will pop up this this edit box where you can provide the valve depth. And in this case, we can input the valve depth. We can input 7,000. That the valve is located, the gas lift valve is located at 7,000, and we'll proceed with that. Okay. So how do we do that? We go here into the software again. The well data, and the gas lift configuration. Instead of using poor boy, let's say it wasn't poor boy and you had actually valves, so you select the valves, and then it will pop up automatically this valve data editor for you. And we're going to provide the depth of the valve. So we're going to say that the valve is located, the gas lift injection valve is located at 7,000 feet. Okay, and we save here. Then we've provided, basically, we've said this is where we're injecting. Now, I'm no longer saying that I'm injecting at the bottom of the tubing, which was the poor boy configuration at 7,300, but now I say that my valve is at 7,000 feet. And you can change that value to your liking, actually, whatever you think makes sense. Okay. And then you can calculate bottom hole pressures again. Okay. Now I've calculated it. I can calculate it again here. Just remove this from the plot. Now this is not with a poor boy configuration, but with a valve depth. As I said, this is a valve depth of 7,000. And you can try different things. You can try maybe increasing this valve depth to like 5,000, and you can run it with 5,000 as well. Whatever the valve depth that you have, you can input, but this is also something that you can play a little bit with as well. Okay. Now, one thing that is very special with the software at Whitson, I don't think we've heard that there's many other software that have this, is the capability of inputting multiple valves versus depth. And I think Stian mentioned this in the theory part. Basically, let's say you're injecting through tubing, so you're producing through tubing, and you're injecting through the annulus here. And then you'll have basically the possibility of specifying, which most of you have, specifying the depths of the gas lift injection valves in the software. And the way it works is that you don't only specify a valve depth, but you also specify the opening pressure and the closing pressure of those valves. And in the software, what it's going to do is that for each time step, it's going to look at what you've specified here, and it's going to say, depending on the surface casing pressure, this PSO is pressure surface open, and this is pressure surface close. And this is basically, it's going to look, the software is going to look at the surface pressure at each time step, and it's going to determine which valve is open, and the gas is going to be injected through the first valve that it finds open. Okay, so that's something that we can specify in the software now. We're going to go ahead and add 3 valves instead of a single valve at 7,000 feet or at 5,000 feet that we had. We're going to say now we have 3 valves. The way to do that is in the software. Again, you go here, gas lift configuration, edit valve data, and you're going to add joints here. You see here, if you click here, when I have more than one valve, then it automatically adds my PSO and PSC columns to tell me to allow me to enter when the valves are open, which valves are open at which pressures. Okay, so in this case, we said we're going to have 3 valves. I think we said 3, 5, and 7. So we start with 3, 5,000, and 7,000 for the valves. And we enter the PSO 1,100, 942. So this is 1,100, 942 for the first valve, 854 and 834 for the second valve, but 855, 834 for the second valve, and 782, 762 for the last one. These pressures here, as I said before, they're going to determine these pressures. They're going to determine which valve is open at a given point in time. So the software, every single day, we have a casing pressure, right? And that casing pressure, the software is going to use to say, at this day, based on the pressures that you have specified in your valve data, these 2 valves will be open. And in such case, it's going to inject through this. And if these 2 valves are actually not open because the pressure is not large enough, then it's going to inject through this one. There's also an additional option, which is this last valve always open. And that's basically that if there's no pressure, not enough pressure to open any of the valves, then the last valve will be always the kind of final escape of the gas. Okay, you should have these values entered. I just put it, hold on the screen here for a couple of seconds for you to enter. If there's any questions, just feel free to ask. Okay, so we just save that and then save the wellbore configuration. And you'll notice actually one thing that I forgot to mention is that you'll notice that here on the top right, next to the calculate bottom hole pressure button, you'll see that it tells you that something has changed. It tells you, I'll zoom in a little bit here, and it'll tell you inputs have been changed since your previous simulation, since your previous calculation. Okay, and it's telling you that for the first wellbore configuration, the gas lift data has changed. So that this little warning here is just to tell you that the data that you're looking at here, the calculations that you're looking at here, are actually not updated with the latest values that you've input. You need to just update, and if you click calculate bottom hole pressures now after that update, you see here it says, I'm going to say now, same values as used for the previous simulation. So that means that none of the inputs have changed, and you're good. Then the results that you're observing here, they are consistent with your inputs. Okay. Are there any questions or comments? Matthias, is there something in the chat, or are we good?
Looks like we are good. It's too easy for them now.
Yeah. I hope so. That's the objective of the software, to make their people's life easy. Okay. Awesome. So, and I do realize I'm going very slow at this, and it's on purpose, actually, just to make sure that people who have not done it, they don't fall behind. And I know there's people here that are actually experts. They know better than us some of the features of the BHP calculation. Okay. And then we have the last configuration that we're going to go through for this gas lift part, and that's the automatic configuration, right? And this is what Stian was talking about in the theory part. Basically, when we define the gas lift configuration to be automatic, when we say poor boy, we say, hey, it's flowing, the gas is flowing through the end of the tube, it's flowing down here, bam. When we specify the valve depth, then we're saying, this is where the gas is going to flow into the tubing. That's it. There's no like magic there. We specify it. We can specify also the PSO and PSC to say which valves are open, and that's it. But with the automatic calculation, what we're doing is that we're calculating a pressure gradient on the analyst side, and that's this red line here. And we're calculating also a pressure gradient on the flowing side. Like on the injection side, we calculate the pressure gradient, and on the flowing side, we also calculate the pressure gradient. But the pressure gradient that we're calculating on the flowing side, that is taking into account the gas lift. So it's already lightening the fluid with the gas that's added from gas lift. And what we do is that we try to find an intersection between those 2 points, because physically that's what is supposed to happen. The gas will actually, if there was a possibility of entering anywhere, it will enter wherever those 2 lines cross, when the pressures are equal. So that's how we determine that. And then in the worst case where we don't find an intersection, then it's going to go to the end of the tube. Okay. So that's the automatic configuration, and that's something that we can very easily change here in the gas lift configuration, going from what we have now, which is valves, to automatic. So I'm going to show you how to do that. Gas lift configuration. Now you go to automatic here. And then there's no need to input anything. There's no need to input. In poor boy, there's no need to input valve depth because it goes to the end of the tubing. And here there's no need because it determines automatically the depth. One thing that we've heard some people have asked for, just in case someone also is interested here, that you can say, hey, I would also love to have that, is in the automatic gas lift method. Some people have said that when they're doing, for example, the nodal analysis in Whitson Plus, they would like to know what's the injection depth reported. The reason I say that they've asked about it in the nodal analysis is because in the nodal analysis, you're looking at one point in time, and you're doing the analysis there. And so you can specify, you can look for that injection depth versus, for example, when we do the calculation of bottom hole pressures versus time, then you basically have an injection depth every day. Every day, the injection depth might be changing depending on the conditions. So that's something that at least people have asked about, that if we could report in the nodal analysis at least the depth at which the gas ends up being injected when we have the automatic gas lift configuration. Okay. Go here, change the gas lift configuration to automatic. Save. Again, it's going to tell you that something has changed. You see, it tells you now that the valves have changed because now you don't have valves anymore. And then you can calculate. Okay. Anyone fallen behind or has any issues with getting to where we are now? Just to recap real quick, so we've done basically with the exact same well, with the exact same wellbore configuration, with the exact same well deviation survey, we've just changed the gas lift configuration from poor boy to valves, using a single valve, using multiple valves versus depth, and also the automatic gas lift configuration. So that's what we've gone through now. Any questions, comments? Okay. Should I take a quick break, Matthias, or is it?
Break time.
We can take a quick break now, and then we'll continue in. We come back in 10 minutes, maybe. 15 past 10. Is that in Houston?
Yeah, and 15 past 9 in Calgary. Very
Awesome.
good. Back in
Okay.
10 minutes.
Back in 10 minutes.
Okie dokie. So we'll get started again. And I think probably haven't run an hour left of content here, and then there will probably be, there's a little bit of Q&A, that's fine as well, and we'll probably end the course a little bit early, but that's totally fine. Main objective today is just to make sure everybody's run through kind of the mechanics of the most important BHP calculations, because that's what we see time and time again is not the most difficult thing, but it's just, you know, it's a lot of information, and it's really tricky even for people who work on this every single day to be able to grasp everything and be able to sort everything out in your head. At least for me, maybe not for Mo. So I'll leave this to Mo, and you take it from here, bro.
Thank you, thank you. So now we'll jump up on to the next well, actually, and this will be well where we're gonna do BHP calculations, but now with rod pump. So for that, we're gonna go to the software here very quick. And also for those of you who are not familiar with that, here in the top bar of the software, when you are in a given well, you can click here, you can switch wells, like it's like a drop-down list, but this list is also searchable. That's something I've seen some people. So if I search like rod pump like this, in this case, I only have 4 wells, so it's not really relevant, but just so you know that you can search on this list. And I know I've seen many people that don't realize that you actually can search in this list. The same for the projects, actually. You can search this list at any time. Okay, so what I'm going to do is I'm going to go to the rod pump well. You can switch from here, or you can do it actually going to the well list here on the left and just go to the rod pump well on your project. And in this case, what you're going to see is that we have also the production data versus time. But in this particular case, we also have, if you click on the edit button here at the top right, the production data, edit, you're going to see that we also have not only surface rates and pressures, but we also have liquid levels. In the previous case, we had gas lift rates, and in this case, we have liquid levels. Okay, those liquid levels are basically the liquid levels that will apply when the rod pump is installed. And you see here we had basically a day where there was a shut-in, and the rod pump was installed, and we started to have liquid levels. Okay, so that date is the 5th of March 2015. And if I go to my bottom hole pressure calculations here, so click on the bottom hole pressure here on the left, make sure you're on the rod pump well, not on the previous well, which was the gas lift, but now on the rod pump well, and open the well data card. I'll open edit well data here. Now, I think, I don't remember who was it that asked the question before about the deviation survey. So now you see here, this is a full deviation survey, maybe a couple of 100 points on this deviation survey. And that's just a matter of copy pasting that deviation survey into here, or mass uploading, which is something that we're going to do at the end of the course. I'm going to show how to do the mass upload, which means uploading this data for 100 wells if you want. Okay, hundreds of wells. Okay, so now with it, deviation survey is already pre-populated for you. We don't want you to be kind of entering every single one of these points. Top perforation, bottom perforation depth is already pre-populated for you. If you go to review the plot of the deviation survey, you're going to see it here. I think there was a question also about the perforated interval, that it shows up like this. In the previous example that we were showing, there were just not enough points to show the perforated interval, but here you see it. So here it shows you both how the well is deviated and specifically which parts of the well are perforated. And as Stian talked in the course, the calculation of bottom hole pressure is done from that top perforation depth. And if you said, okay, actually, I want to make it from the bottom, then it's just a matter of changing this. You make this very close to the bottom perforation depth, and then the calculation is going to go all the way to the toe of the well. Okay, but right now it's going to be closer to the heat. Okay, so that's already populated for us. And then when it comes to the wellbore configuration, the well actually for the first period of time before this 5th of March of 2015, it was flowing through casing. And that's what we have here. That's the configuration that has been input here. And now what we want is we want to tell the software, hey, at some point you need to change this configuration and start using another configuration, which will be rot pump. Okay, how do we do that? We need to add, we don't want to edit this configuration because this configuration is valid for a certain period of time. We just add a new configuration, and we do that with this plus button here. Add new wellbore configuration. Okay, I'm going to say now I want to go and have a new wellbore configuration. And you see the first thing that it gives you, it tells you, give me the date from which I should start using this new configuration. For the first one, it doesn't ask you for a date because that's the initial. That's from time 0. The second one, it needs to know, when do I switch to this one? You just have to provide that date. And if I go back, if you remember from the production data, it was the 5th of March, 2015, but I can just go quickly here into the slides. So add a new configuration. And you'll see here, we need to provide the 5th of March, 2015 as the date. Okay, so we click here, and a quick trick, you don't want to suffer through going month by month here back to 2015. What you want to do is you want to click on the top here where it says April 2023 one time, then it's going to take you to 2023 and give you all the months of 2023. But if you click on the year now, 2023, it's going to take you to the year selector. So now you can select which year you want to go to. You just scroll down to 2015. Okay, then you know which month we wanted. If I go back to the date, we want the 5th of March, 2015. We go to March, and I select the 5th, the Thursday there. Okay. So that's what I have. I provide a new configuration. I say which date they should, it should start using that configuration. And now with this configuration, I know that the well is on rod pump, so there has to be a tube in there. So this is what's shown here on the slides. You have the information related to the tubing. Okay, right now we have 0, and here we have 0 tubing. We have no tubing strings at all. We just click on the plus button to add a tubing string. So click on the plus button here, bam, that adds a tubing string for us. Okay, and then we input the data for this tubing string. We put the bottom, basically the landing depth, the internal diameter, the external diameter, and the roughness. Okay. You can also go and use the catalog like we've talked about before. You can use the catalog here. We saw it was a 2 7/8 tubing. So we go here, and the inner diameter was 2.44. So it's this tubing here. Just click there, populates it there. And the bottom MD was 7,022. 7,022. That's what I want. Okay. So now I've added a tubing string and provided the information about the tubing string. And now I want to switch the flow path. You see now, if I have my flow path being casing, if I say I only have casing installed, if I'm flowing through the casing, basically, it's going to tell me there's no artificial lift, there's no valid artificial lift method that you have. It hides my artificial lift selector here. Now, if I switch to a valid method that can be used, a valid flow path that can be used with artificial lift like tubing or annulus, then you see that this artificial lift selection drop-down pops up. Okay, in this case, we're going to use tubing. And the artificial lift method that we want is rod pump, right? Okay. So just remember, we're not editing the first configuration. The first configuration is still here. You can access it by clicking just above the number 1, wellbore configuration 1, initial. Click there, you still access the old configuration. This is the configuration that's used from the beginning of the life of the well until the second one kicks in, which is on the 5th of March, 2015. And I might have had another configuration coming up like later. Maybe I went from this to, I decided to implement gas lift. Then you just pick a new date and go to gas lift at that date, for example. That's not what we're going to do here, but this is just an example for you to see. You can have as many configurations as you actually have in the well. Okay. I'm going to delete this one here. So this third configuration I just added for showing you a quick example. I'm going to delete that here. Go back to the second configuration. Okay. You should have the second configuration with this date, with this tubing data, and this artificial lift method. And then you can save. Now that you've saved, you can calculate bottom hole pressure. You can click on calculate bottom hole pressures. It should calculate pressures for you. You see here that you have the pressures calculated through time up to the 5th of March. Then it also starts calculating these new pressures that are the pressures calculated with the rod pump method. Okay. So we've done this now, and just a quick reminder of how rod pump calculations work is that we basically divide the well bore into 3 segments. So we start from the top perforation where we know the surface pressure, and down from the top perforation down to the end of tubing, we do a regular multi-phase pipe flow. So there we use the multi-phase flow correlations. Then from the end of tubing to the liquid level that we've specified with the production data. In this case, the liquid level was 5,500. We go back here, production data, liquid level here. For every single day, I have a liquid level. Okay, so that liquid level is going to tell me that basically the height of this liquid column. That's a liquid column that has some gas flowing through it, like with some bubbles flowing through it. Stagnant liquid column with some bubbles flowing through it, like Stian showed earlier. And then from that top of the liquid level to the wellhead, then it's just single phase gas flow. When you say nothing flows there, it's only gas. That's how we do the rod pump calculation. I think that's pretty much how every software in the industry does it. Now, if you go to the bottom hole pressure calculation here, you're going to see that you have the period before the rod pump, then you have the rod pump period, and in this period, there's something strange happening here, right? Like in this, there's this bump, this kind of increase in pressure right here around 18th of March. If I change from dates to days here, if I toggle this, then it tells me in days it's around day 77, 78. There's something that is making my pressures go up. Okay, I look at it in the presentation here. So what do you think is happening here? Anyone has any thoughts on what might be happening here? Why is suddenly my pressure jumping from, what was it before, like around 700 psi up to 2,800 psi just for a couple of days?
Some maintenance on the rod pump, it was removed, or?
Yeah, that could be. Well, we can actually just go, and how do we find out what's going on? We try to go into the input. So we go into the production data, and we see, okay, what happened during those days? So here we have, if I go back just real quick, it's March 18, March 19, or if I switch to days, it's 77 and 78. Go back to the production data, maybe dates. You see, this is March 16. You see how the GOR, March 17, then the GOR just drops. There's no GOR, there's no gas rate, basically, in this period. You see what's happening? Basically, the gas rate disappears, and some issues maybe with the measurement of the gas rate. And the good thing is that in the software, in Whitson Plus, we have this capability of smoothing the rates, of smoothing actually all the inputs, all the production data inputs, anything. It could be the tubing pressures, the rates, casing pressures as well. So what we can do now is we can say, hey, this is not real. Like this, the fact that the oil rate is not changing at all, the water rate is not changing at all, but my gas rate suddenly disappears. There must be something here. Like it's just an error in the measurement, in the recording of this measurement. You can just click on the smooth here on the production data tab, top right. Okay, and this will allow you to basically pick which data set, which production data set you want to smooth. In this case, I want to go to the gas rate. Okay, and I know that it was somewhere March 18, so I can zoom in here. This is between March, I think it's somewhere here. This is March 17. You see March 18, 19, there's no rates, and then there's suddenly another rate at March 20. So what I'm going to do, I'm going to use this smoothing functionality, and the way it works is that I can add points, and it's just going to do a linear interpolation between any 2 points that I add. In this case, I can add a point here for this one, and a point here for this other one. I think I just have to move them here a little bit. There we go. And what it's going to do is going to create a set of rates for me in between these two values, just to fill it in. This I'm doing between these 2 points only, just for the illustration purposes. You can actually do it in the entire through the entire data set. You can click, if I click out of it here, then it will create a smoothing function for me. I can show you just that real quick. You do out of it, it's going to create a smoothing function. I change the sampling frequency maybe to 5. It's going to smooth those rates. If you have a lot of outliers, you see then suddenly it removes those outliers, and I can adjust that smoothing if I want by adding more points wherever I feel like it's necessary. Okay, in this case, I don't want to go and smooth the entire thing. Just wanted to show you that even if I have a specific part where I want to fix an issue with the measurement, then I can do that by just zooming into that part like here and adding the values. Okay, adding the points, and just I just add the points here.
Well, how do you switch between days and the date?
Yeah, good question, actually. Let me just show you that. So if I save here, it picks it up from here. If I go dates, date. See here, this is
okay.
toggle in the production date.
Got it. Thank you.
Okay, so now you see I've already smoothed that rate. Now I said, okay, fill this gap. And then I also have to tell the software to use the smoothed data, because I could fill the gap, but decide not to use the smoothed data. So this is, you have to tick it here, use the smoothed data, use the gas rates that are smoothed, and then you save. And then basically it fills this gap that was, I think, here between somewhere here. I had a gap between March 16, 17, and March 20. I had a gap, and now it's filled with actual gas rates. Okay, and if I went back to the bottom hole pressure calculation, this is where the jump was happening, and I tried to calculate again. You see here also, it's going to tell you again, something has changed. Another input has changed. Now we didn't change any input in the well data like we did before, but we did a change where? We did a change in the production data. We adjusted the gas rates, basically. Okay, so the software is going to also tell you, hey, something has changed, so the stuff you're seeing here is not really updated. The numbers that you're seeing are not updated, so you just calculate bottom hole pressures again. When you do that, hopefully that will remove that bump that we saw for the gas, that was basically caused by the gas rates. Okay, that's one thing about the smoothing. That's in the production data. There's also one functionality that many people also are using, and that's what we call the custom PWF, custom bottom hole pressure. And that's basically taking the bottom hole pressures that are calculated here, and since those are very sensitive to noises in the production data, for example, you can, instead of smoothing the production data, just smoothing the bottom hole pressures. We generally recommend, if you ask Stia, for example, we would recommend smoothing the production data instead of smoothing the pressures, but it depends on what people really like. But here I can do basically the same, but now it's on the output. This is on the calculated pressures. I can go ahead and say, okay, I want to do the same. I want to create either fill a gap or create some sort of auto fit smoothing function that will allow me to remove some of the noise in the data. Okay, so I could have done something like this for the part where I had the jump in pressure. I could have done something like this as well. Okay, I'm not going to do that now, at least. Yeah. Was this clear, like about how you smooth the gas rates or how you smooth any data set?
Could you just go through the thing again, please? Sorry.
Yeah,
Didn't
no
catch
worries.
up.
Of course, no worries at all. So what I did, I can just do it again very quick. If I went, what I had is that I just calculate bottom hole pressures again with the unsmoothed rates. Okay, so what I had is something like this. I have an issue with my pressure. Something is off. I go to my production data. I find that, well, at this point, there's no gas rate. It's just gone, the gas rate. So my GOR is going, it's becoming very, very low. And, or it's non-existent. And then, then I go here and I say smooth, and I pick the gas rate that I want to smooth. And I know the period that I want. In this case, I need to just go back and check the period. So it's between day 76 and 79. I go here in the smoothing, pick the gas rate as the production data that I want to smooth. And it's between 76 and 79. So it's between these 2 points that I want to fill the gap. So I can zoom in here just by click and drag in the plot. Just like this, I can zoom into any section of the plot. So now I'm zooming just specifically to this part. Okay. Once I've zoomed in, then I'm going to click on this icon here to add points to the plot. And this will add points for the smoothing. So this is what I'm going to kind of construct this piecewise linear trend that is going to be used to smooth this data. So I'll just click on this, and then I can decide to add points wherever I want. In this case, I want to add the points, 1 point here, and I want to add another point here. And basically, you see that this yellow line is basically the piecewise function, basically, that's going to fill the gap between these 2 points. So the gas rates between these 2 points will be filled with the values in this yellow line. Does that make sense?
Yeah, it does. Thanks.
Perfect. And so once you do that, then you click, you have to select it to use the gas rate, by the way, don't forget about that. Use the smoothed gas rate here. Because otherwise you're going to be applying the smoothing, but not using it. Okay, so then you use it and then you save. Once you do that, your gas rates will update and you're going to get the GOR for that period. And then you go into the bottom hole pressure calculation and relaunch that calculation with the new smoothed rates now.
Got it. Thank you.
Awesome. Perfect. So now we've gone through what was happening there and then also how to fix it. We go and smooth the data. Okay. And this is something we see actually very often. Like I think there's even people like Mark and others in the call that have a lot of experience with this issues with data, with input data, and how to go about it. So the next thing we're going to go through now is how to do the calculation when your well is on ESP. And there, Stian already talked about it. Is like you have basically the ESP itself. We're not doing any pumping calculations themselves, but all what we're doing is that we're leveraging the fact that the ESP has a gauge at the inlet, a pressure gauge at the inlet of the ESP. Okay, so what we do is that we say to the software that now I have the pressure at this point, and the only thing that I have to do is calculate the pressure from this point down to the top perforation. So it's generally a fairly short interval that we need to calculate the pressure drop across, and we specify basically the gauge depth to tell it from where to do the calculation, and that's it. Okay. So in this case, we need to go to the well with ESP. We need to change the artificial lift method. That is going to activate this calculate from gauge to sand face using measured pressure, because it's going to activate the correction basically that we're talking about. It's going to correct the gauge pressures measured from the ESP down to sand face pressure. And then we need to provide just this depth, which is the depth at which the ESP gauge is installed. Okay, the depth at which the ESP is installed, basically. Okay, so we can go into the software. Again, you can switch wells here from the top menu, from the top bar, and now switch to the ESP well. Okay, and in the ESP well, we're gonna open that card. We're gonna see that we have the deviation survey again, full deviation survey populated. Like copy paste from the entire deviation survey. There's no need for an abbreviated or short version of the deviation survey. Just the whole thing copy paste here. You see the deviation survey plotted here with the perforated interval. And then in the well data, the question that was asked about setting the two casing strings, one where not both of them go to the top of the well, and this is the case here. Basically, you have one of the casing strings going from the top down to 8,000 feet, and then the second one hanging at 6,000 feet down to the heel, to the toe, sorry. Okay, and so that's already input here for us. And then we have also the tubing information already input for us, because we've in the previous exercise we've done this, so we don't need to repeat the input of tubing data. Okay, what we need to do though, which we haven't done before, is change the artificial lift method to ESP. And I want you to pay attention to what happens to this switch when you do that. Like this switch here, you don't touch it, but let's switch from artificial lift none to ESP. Just click here ESP, and you'll see that this switch gets activated automatically. Okay, because that's the whole point of ESP, is that when you have the ESP, you want to convert from gauge pressures measured at the ESP inlet down to sand face. And here we just have to input the depth of the gauge. In this case, it's 8332, so the ESP is at the bottom of the tubing, basically. It's the same as this. Okay, so 8332. Okay, so what this is going to do, it's going to say, now I have a pressure at this depth, and it's going to try to convert that pressure down to this depth, to the top perforation. Okay, that's all the calculation we're going to do in the software. It's a correction from the measured gauge depth down to sand face pressure. So input that. This should be activated. It's activated automatically when you pick ESP, and then save. And now a quiz question, very quick. Is when I calculate bottom hole pressures, before you click calculate, is the pressure calculated going to be above or below this gauge pressure? Just write it in the chat. Is it going to be above or below? Before you click calculate, if you click calculate, you're cheating. Above? Good. Awesome. There's consensus at least. Yes, very good. And the reason it's going to be above, anyone wants to try? If I run the calculation, it's going to be above, because I'm correcting. If I go back here, I have a pressure here, and I'm just correcting that down to the top perforation. And the difference between the gauge and the actual calculation will be as small or as large as the difference in depth. So if I had my gauge, I went here and my gauge depth was higher. If it was like 7,000, then the difference would be larger between the gauge pressure measured and the actual sand face pressure. Just run this at 7,000, for example. You see that it becomes a larger difference. Okay, but it will always be above. Any questions? Just correct it back to the correct depth. Awesome. So now I'm going to show you one thing that actually Mark, that is in the call from Diamondback, he requested that we implement in the software, and it's a very clever thing to have, and that's the BHP calculation settings. Okay, and what we're going to do is that we're going to go back to the gas lift well that we were working with, and we're going to open the settings here on this BHP calculation settings, and we're going to look at that, and we're going to look at how that affects our calculations. We're going to go here, back to the software, pick the gas lift well again, okay? And in that gas lift well, we're going to open the well data card. So make sure you're in the gas lift well, open the card where you edit the deviation survey and the well data. And at the top here, you have like a small gear wheel, like a settings icon. And that has the calculation options. Okay, all right. If you click on that, in this case, we know these are the defaults that we have. So what we're saying here is that when we have gas lift, do we want the software to calculate a pressure when the gas lift rate is 0? By default, this is activated. This is on. So we're saying, yes, calculate when the gas lift rate is 0. And when we have rod pump, if we want the software to calculate when the liquid level is 0. By default, that's yes as well. And then the final one is when we have ESP, if we want the software to compute pressures when the gauge pressures are 0. And that's by default off. Now what we're going to do is we're going to try to turn off the gas lift one, because this is the gas lift well. We're going to try to turn off the gas lift one and then save the well data as well, and try to run. You see, again, you get the warning that something has changed, and you try to calculate the bottom hole pressures now. You see what's going to happen there. Okay. So you see what we get now. We get, if I remove the gauge pressure, you get periods of time where there is no calculation at all, no bottom hole pressure calculation happening. Okay, and the reason this is happening is because in our case, the way we set up the configuration, we set it up as a single configuration that we have with gas lift, and in that single configuration with gas lift, if we have the option here ticked, whenever the gas lift rate is 0, it just doesn't do gas lift. It just flows regularly through tubing. Okay. So this option can be useful, but you need to be sure, make sure that you are using the correct configuration with it. Because if we had ticked off this, then we basically here would have to have 2 configurations to get the correct calculation. One configuration without gas lift and one configuration with gas lift whenever the gas lift came on. Okay. A lot of people we see, there's actually a bit of a mix. Some people like to do it this way, where they merge the gas lift with their existing configuration and just say, okay, whenever the gas lift is 0, just use the configuration as is. But maybe the other half of the people don't do it. Most important is that you're consistent. The calculation settings should be consistent with your wellbore configuration. In this case, in this particular case that we're running here, it doesn't make sense to turn off this setting here because of the way we have configured the well. Okay. So I rerun now with the correct settings, and that should be good. Okay. Now, for the other one, there's no need for you to follow this. I'll just do it for the sake of the example. The other configuration is on the rod pump well. The other calculation setting is on the rod pump well. And what that says, if I go to the rod pump well, it's the same set of settings, but that we want to apply it to the rod pump, and it says that whether we should compute when the liquid level is 0. Okay, and so let us go. In this case, we have 2 configurations. We've already said that rod pump does not apply before the 5th of March, so we're already forcing that. But let us go into the production data and say, okay, where is the rod pump coming in? It's in the 5th of March, so that's correct. Let's just remove some of these liquid levels here. some period, whatever period we decide. It's just for the sake of the example. You don't have to follow this, just see what's going to happen. If I remove, now I have a period where I've said to the software, hey, this is flowing on rod pump, but there's no liquid level provided, okay? And what does the calculation say? The calculation says compute when liquid level is 0. So still make the calculation even if the liquid level is 0. If I do this and calculate the bottom hole pressures now without the liquid level, you'll see you'll get some portions of the data that just don't make sense. Because this is supposed to be a rod pump calculation where the liquid level is going to determine a large amount of the pressure drop there, and now that liquid level is non-existing. But most likely, if you have a rod pump and you don't have a liquid level, most likely it's because of an error in measurement. You just didn't input the liquid level, etc. This is not really your pressure. So in this case, either you input, you find the liquid level and input it, or like our friends at Diamondback are doing, you just deactivate this one. You say, okay, whenever there's no liquid level, don't calculate, just skip it, skip that time step. And that's what's going to happen here. If I calculate bottom hole pressures, now it's going to skip this, and at least it's not going to give erroneous pressures. And that was the main objective, I think. Mark, feel free to jump in and provide your input here. You were the one who requested this, but I think the main objective was to not give the user a bottom hole pressure that was wrong. You'd rather not have a bottom hole pressure calculated at all than a wrong bottom hole pressure.
Correct, and it makes it easier for us to smooth if we choose to do it with the correct bottom hole pressures.
Correct. Yeah, that's true as well. So what Mark is saying is that basically, if I had this jump here like I had before, then if I went here and I wanted to do some smoothing, I just change this, and I wanted to do some smoothing here, then let me just remove some points here. Yeah, and I wanted to smooth here, then it would have been heavily affected by that jump that was not real. While here now I can just do this, and suddenly I have a fairly okay bottom hole pressure throughout that period where I didn't have liquid level. The same could apply. It's kind of smoothing the liquid level. You could just pick the 2 points where you don't have the liquid, or the 2 points around where you don't have the liquid level, and just use some liquid level there. Would have had a little bit of the same effect. Okay, very good. Are there any comments or questions here? Good. Yeah. So we'll go to the next part of the exercise, and here we're going to be doing tuning of the BHP correlations to the measured gauge data. So we have, in this case, we're going to say, okay, we have a well where we have a gauge downhole. We have measured that pressure. So this is the gauge pressure that we have measured. We have it there versus time together with the surface rates. Now we want to go ahead and compare how the software calculates with the correlations that pressure. And then we're going to want to do some tuning to those correlations to match that gauge, that measured gauge pressure. Okay. So what we're going to do is we're going to go into the software. Now we're going to pick the last well in the list, this BHP correlation tuning well. You see here. You click on that. Here you see that you have the gauge pressure that has been input. In this case, for this particular example, we're assuming, okay, this gauge pressure is actual gauge pressure. It's measured gauge pressure that we're going to be using for the tuning. Okay. And as you can see here, like we've already populated the top perforation, bottom perforation, deviation survey, everything is looking good. And then we go to well data. And in the well data, you see that everything is populated, like the casing data. Again, here you have 2 casing strings kind of intercalated into each other. You have the tubing string. You have actually even gas lift with a single valve in this case, but with a specified valve depth. And all that is good. But what I want here, the objective of this, all that we've gone through before, the objective here, we're trying to say we want to tune those correlations. We want to check how the correlations do against the measured gauge depth. So the measured gauge pressure, sorry. And for that, we have to provide a depth for the gauge. Okay. So in this case, if I go back to my presentation, the gauge depth is going to be 7595, which is the same as the tubing bottom depth. So we go here, just input that gauge depth here. Okay. That gauge depth is not going to be used, at least in the main bottom hole pressure calculation, unless I tick this, but I don't want that. I don't want to calculate from that gauge to sand face, but I want to keep this gauge depth for my tuning that we're going to be looking at just in a second. Okay, so we save here. Just make sure you put the correct gauge depth here again, just to show you 7595 is the gauge depth. Nothing else changes from what was there before. Okay, and we save. We can calculate bottom hole pressures. Okay, I will see that the calculated bottom hole pressures are all falling, just the calculated are all falling below the measured gauge pressure. Okay, and if anything, they should fall either on top or be higher, because we know that the gauge is set at 7595 depth, and the top perforation is at 7800. And that means there's about 300 feet of difference between the gauge and the top perforation. So the pressure at the top perforation should be higher than the gauge pressure. Okay. So how do we fix that? Now we say, okay, something is off with these correlations. No, it's not working. Okay. So we go and we say here at the top right, we click on this tuning button here. And what this is going to allow us is going to bring this dialog for tuning that Stian talked about, and that has basically two columns: one liquid holdup correction column, this alpha term, and one friction factor correction column. And the rows represent each of the correlations, so you can apply a correction to each of the correlations individually. And what we're going to do now, we're going to ask the software to tune the correlation to the data. And here's where the gauge depth becomes important, because it's going to use, it knows that the gauge pressures that you have provided, they are at that gauge depth. So it's going to compute not to the top perforation, but it's going to compute to the gauge depth, and it's going to compare against the input data. So I just click tune and just read this here. It says that if you tune the correlations, then the tuning will overwrite the current tuning parameters. That means that those new tuning parameters will be applied to any further bottom hole pressure calculations done with these with this correlation for this well, at least. Okay, so that's fine. If I click yes, then it's going to start tuning.
If you want to revert back to, say, you don't like where it went, if you want to revert back to the original, can you do that?
Yes, very good point. Yes, you can revert back to the original. Actually, that's simply by just writing here 1 and 1, because we said those are multiplies, right? So if you just get them back to 1 and it's saved, then it's reverted back.
Of course. Yeah. Sorry.
No, it's a very good question, because I think a lot of people also forget that you can edit this. And the other reason this is important to know that you can edit it is because you might have a well that doesn't have gauges, where you don't have the possibility of doing this tuning, but you did a tuning on the neighbor well. You know that the Hagen and Brown should have these correction factors for your pad, for your area, and then you just come here and paste those values here and save, and those will be applied for this well as well. Okay, so you click tune, yes, and then it's going to start doing the tuning for you, and it's going to come up with some factors, the correction factors for the liquid holdup and for the friction factor, and you can do that for each of the individual correlations. And in this case, let's do it for the 4 correlations just to start with. So just go one by one and click tune and yes. And you should see basically it should take 2-3 seconds for it to calculate the correction factors. And it's just trying basically to come up with which correction factors will help us match better the data. If I click now, after I've done tuning on all of them, if I click on show fit here, I'm going to see the fit that I'm getting. What the software is trying to do. So here you see it's the comparison of the pressures, but these are at the gauge depth. notice these are not sand face pressures. These are a little bit higher than the sand face. These are at the depth of the gauge that I have specified. And now it's saying, okay, if I calculate pressures down to that gauge depth, this is what I would see with the different correlations, and this is the measure. The black is the measure. Okay, you can see that it's trying to do something. It's kind of trying to match around the black line for all the correlations, but you can see also consistently that for all the correlations in the early time, it's just under predicting. It's like consistently under predicting early time, consistently under predicting early time, consistently under predicting early time for Hagedorn and Brown. So basically, all the correlations are trying to do something later in time, maybe for better or for worse. But all of them early time are first falling on top of each other and under predicting compared to the gauge data. Okay. So what do you think here? Did you pay? Let's see if you paid attention to what Stian was saying in the theory part. What do you think is happening here in this early time? Just unmute or write your answers in the chat. Yeah. Very good. Yeah, exactly. You know, typically in the company, whenever something, whenever someone asks what's happening here, the first answer is Mo. Yeah, very good. So actually, Reza, that's I really like. So it's basically single phase flow that's occurring there. So there we're still during these time periods, the conditions, pressures, rates, temperatures are such that the wellbore is all filled with single phase fluid. So we don't have two phase flow in the wellbore, at least for most of this period. So all the correlations, when it's single phase flow, all the correlations will first predict the same pressures. But also we have made a decision to not weigh those points for tuning, because in this single phase flow region, and whenever you're in single phase, it doesn't make much sense to adjust the multi-phase flow correlations, because we know that there's in the single phase pressure drop should be fairly accurate. Instead, what we should be thinking about is something is off with my single phase flow. Okay, and what has a larger effect on your single phase flow is going to be your densities. We have densities of three main phases that are flowing in the wellbore, and that's we have the oil and the gas densities. Those are coming from our PVT definition. It is possible that your PVT is wrong, so that's something that you can revisit as well. Okay, let me check if I had the wrong GOR in my PVT, if I had the wrong composition, or something along those lines. But let's say your PVT looks good, you're happy with your PVT, then the other thing that you need to check is your water salinity. And that's very important to check your water salinity, because in Whitson Plus, you have the possibility of editing the water salinity, but that's by default 0 ppm. Okay, so whenever you're doing tuning, if you have a single phase region, always start by adjusting your water salinity. Okay, you might have a value for that. If not, you can just try to adjust it iteratively, because who knows what the actual value is, for example. So we go into the software and we're going to be adjusting the water salinity. And what we're going to do, Matthias, you want to say something? I think you're muted. Yeah, okay. Yeah, so we can go now, just for the sake of the exercise, we can go into the software and just try to adjust the water salinity. We're going to try to change the water salinity iteratively and see if we get a better match for this single phase region. Now, the water salinity is going to also slightly affect your multi-phase flow region, and therefore your tuning parameters will change as well with the water salinity. But that's fine. It's a little bit. Okay. So we're going to focus on one correlation only. Let's not try to tune all the correlations, like it's unnecessary. let's just try to adjust the water salinity, focusing on the Hagedorn-Brown correlation, and just change the salinity on your end. Some values, try to do this something similar to what I'm going to do now in the exercise. Just as a reference, seawater salinity is between 10 and 35,000 ppm, and brine salinity is above 35,000 ppm. Generally, you could say up to 250, maybe, or even higher salinity, 300,000 ppm is okay as well. Okay, so how do we do that? How do we adjust the salinity in this bottom hole pressure calculation? In Whitson Plus, the salinity is actually a well attribute. So in reality, you could go, if you click on this eye icon here, you could go here and you could adjust the salinity as a well attribute. And this will basically adjust the salinity both for the bottom hole pressure calculations and for the numerical model simulations, for like your reservoir simulation. That will adjust it globally for everything. And that's the same if you went into the bottom hole pressure calculation and you adjusted it from there. The bottom hole pressure calculation, you go into the well data. And here you're going to see a small droplet at the top. And there you can edit the water properties. Okay, there you can change the water salinity. So let's just try something. So you just, we had the reference of salinity. Let's start with, for example, 10,000. That's the seawater salinity, a low salinity like 10,000. And we save that salinity. And then we go to tuning and we just tune Hagedorn-Brown, nothing else. And just once we tune Hagedorn-Brown, we get, once we get that value, those values tuned, and we show the fit. Okay, so we show fit. It doesn't seem like it made a big difference in the Hagedorn-Brown. It's still in this single phase region. It's still below my gauge pressure. Okay, so let's just try to go and adjust that salinity further. If we look at the reference again, maybe go to 35. Try that. That's the limit for brine, the lowest brines. Save. There we go. And then tune only the Hagedorn-Brown. You go tune only the Hagedorn-Brown. It's getting there. It's increasing a little bit, but it's not quite there yet. Okay, so we can go and increase it even more. Say to 100,000 ppm. And go to tuning. Tune again the Hagedorn-Brown. There we go. And show fit. You see, it's better, much better now, much closer. If I compare to like where Beck's and Brill was coming with the previous salinity, now it's much better for this single phase region. Maybe it could be increased a little more because it's still below all the time. That's up to you. But basically, what we want to convey from this is that when you have a single phase region like this, you should always consider adjusting your salinity when you're doing this BHP tuning exercise, BHP correlation tuning exercise. Now that I have these tuning parameters that I've converted into these tuning parameters, then you're going to see that it says inputs have been changed since your previous simulation, and it says that now the parameters have changed. So what I have to do is I have to rerun the calculation, which is going to calculate now bottom hole pressures for me, but with the tuning parameters. Okay, that should be much better now when it comes to the gauge. Okay, here we go. I think I would actually, in this case, I would increase a little bit more the salinity. So you could go maybe to, let's say, 150. That's fine. Okay, that's probably going to be better here. Any questions or comments about this?
Yeah, Mo, I have periods where the correlation is not calculating. I have gaps in my data.
Yeah, Matthias, maybe can you go into the, I can actually just check here real quick. Can you go into the project for, is it, yeah, Terran?
Yeah.
Maybe, Matthias, can you go into the project of Terran and double check?
Yeah.
And maybe do it here. What's your email, Terran?
tkashib@marathonoil.com. I see that even in your correlation, there are periods where it's not calculating.
This? Here.
Yeah. If you just look at Hagedorn Brown,
Oh, these
see there
gaps.
are gaps.
Yeah, I think Stian, maybe you have a better idea of why these might be occurring for the Hagedorn and Brown.
Yeah, so we can just look at the tuning parameters real quick. So the thing is that the liquid holdup correction here is quite high. A factor 4 is quite a lot. If it's more than 2, you should be careful. If you amplify the liquid holdup too much, it will be harder for the solver to compute the well pressure down the well. It can make the solver more unstable. So that's likely what's happening in those couple of missing points there. Yeah, if you just submit a ticket, I can have a look at, or just submit a calc ID, I can have a look at it. But
yeah, actually, that's a good exercise to show how you submit the ticket. So if you have any issues with the software, if you have a question, if you just like, okay, something is, I just want to talk about something, then one quick way to get a hold of us is to send a feedback or what we call a ticket. You do that here at the top right on this icon that looks like a comment box. See it here. Okay, so if you click there, the good thing about this, you just provide, you say, okay, why are some of Hagedorn and Brown values missing on calc? And then you say, okay, this is like a question. And the good thing about this is that it sends it to the entire support team, to the entire software development team. It gets assigned a person that will follow up on that. And then everyone gets like a Slack message, an email. It's like gets a bunch of notifications to everyone to make sure that your case is followed. And you'll get a reply, generally, at least a reply that, hey, we're looking at this within 2-3 minutes. And we'll get back to you on that. So the other thing that it does is that it sends us this, which is internal for us, is the calculation ID, which is what Stian talking about, which allows us to go deeper into the calculation details and just debug it in more detail. So Stian, please take a look. Okay, and then if you do that, and you get sent, and then Stian and everyone in the software team is going to pop up with a message saying that we've reported it. Okay. Awesome. Thanks for that question.
Sure.
Yeah. So then I've adjusted the tuning parameters a little, or I've tuned again because I changed the salinity even more, and now I can just calculate bottom hole pressures again, and I think that should look a little better. Yeah, that's a little better here now. Yeah. Okay. That's the tuning part, bottom hole pressure tuning. And what a lot of people do, like I said, is that they do this tuning for a bunch of their wells. Let's say you have an acreage with 200 wells, but you have 10 wells which have bottom hole pressure gauges. You go to the 10 wells where you have the gauges, you try to do this exact same exercise, and you'll come up with some sort of average values. You'll come up with probably some of the values will be a bit of an outlier, but most of the wells are hopefully, let's say 8, more than 7 out of the 10 wells will be in the same ballpark range of the liquid holdup correction and the friction factor correction for the given correlation that you're looking at. And then they apply that correction. They say, okay, this is my field-wide correction, or my correction for this area, or this fluid type for the gassy area of my acreage. And that correction is applied to all the wells, even those wells that don't have a gauge pressure, because that's the whole idea. The ones that have gauge pressure, we know that's the pressure. The ones that don't have the gauge pressure is where we really are interested in doing it. So then you just copy these that you've kind of converged to and paste them into every single well. And in the future, we're going to have the possibility of creating tuning sets, which means that you can save these and call them like whatever your company name, company-wide tuning, BHP set, and then every well that you go to, you'll be able to select from a drop-down which tuning set you would like to use for that well. Okay. Any questions or comments? Perfect. So just an important thing that Stian went through, but I just want to make sure to re-emphasize is that many people, at least when we first introduced the BHP tuning feature, many people tried to use ESP measured pressures, like gauge pressures from the ESP to do the tuning, and that will not work. It's not possible to use pressures measured at the inlet of the ESP for tuning the correlations, okay? Because the correlations, when they're doing the tuning, they're not going to be accounting, like this is actually the pressure profile, how it would look like if you had an ESP installed. What's happening here at this depth is this is where the ESP is installed, that you get a boost in pressure because of the ESP, okay? And the tube pressure that you're observing here is already like a result of that boosted pressure. So you're not going to be able to account for that boosting in your BHP tuning. So it will be very wrong actually if you try to do tuning with ESP pressures. So don't do that. And we saw a couple of times actually people that were trying to do it, and it's actually very legitimate to try to do it. It's just like it's not going to work, unfortunately. Okay. Because most of the people, quite a lot of people have pressures from ESPs actually. Okay. I think, I don't know, Stian and Matthias, what do you think if I just wrap up very quickly with a mass upload and then we should be done?
Yeah.
Is that okay? About 5 minutes? Okay. Yeah. So what I wanted to show you here is that all what we've talked about now, that's like how to input these things manually. But most of you will be working with tens or if not hundreds of wells, okay? And there is actually a much better way to do this, which is through the mass upload sheet. And the mass upload sheet, I can show you just an example of that right here. Let me open that file. Okay. This is the mass upload sheet. This is now showing it. I'm showing it for a single well just to show you specifically the example, but I'm going to show you another one with multiple wells in the mass upload sheet. So here we just specify the well data, which is some people call it the well headers, basically well name, UWI, reservoir pressure, GOR, temperature, and other optional attributes. Okay. Then you go to the production data, you specify the well name, date and time, and then the rates and pressures, and liquid level or gas lift rates if you want. Okay, so this is actually the example that we went through in the course for the rod pump, and you see here the liquid level. Let me just zoom in a little bit here. Okay, that's the liquid, that's the production data. And then you have the deviation survey data. That's for this same well, the rod pump well. You just provide the deviation survey data in this form. And if you had another well, you just write the other well data here. And then the wellbore data, it's provided here. Okay, I want to just quickly show you what will happen if I pull this file into the software. How do I upload it? Yeah, I'll go into the wells, the well list, and I'm going to click on the mass upload here on the top right. So you go to your wells list, which you can get from the left navigation panel, and you click on the mass upload. Actually, if you want to get the template, you can get it from this here, download Excel template. But now I've pre-populated it at least, so I don't need to download the Excel template. But if you want to start working with that, you just download it. Then you just drag the file in here. Okay. And when I click save, that file gets uploaded into the software. And I see it here. And just wanted to show you how that basically gets uploaded with the production data, all the production data that I had in this file. Oh, sorry, it's this file here. all the production data here. That's basically going to be reflected into the software right here. And then for the bottom hole pressures, the deviation survey is going to be coming from the deviation survey tab here. You see there these values, so I don't have to copy paste, they're already input there. And then for the well data, this is the wellbore configuration 1, wellbore configuration 2, and those are provided here as wellbore data. You see, I provide the well name, I say which is the top and bottom perforation, and then I say which is the configuration number. This is the first configuration. The use from date will be empty because this is the first one. It doesn't have a use from date. Then the flow path is going to be casing. That's the flow path that's here. Then the wellhead temperature and rock temperature at surface. That's actually something that we didn't maybe cover here, but that's the temperatures that you can edit here if you want to edit the temperature profile in your well. Okay. And then in this case, I don't have a tubing, so this remains empty. The tubing data remains empty. That's why here it's a 0, no tubing. And I have a casing. The casing information is provided here. That's what's there. And that's it. That's for the first configuration. For the second configuration, then I have a date, a use from date. So if I go here, I'm going to see that uploaded. Use from date. Then I have the flow path, which is tubing in this case. Then I have the wellhead temperature. That's the same. And then I have a tubing now. Tubing, bottom MD, ID, OD, and roughness. Those are provided here. And the casing information provided here. If I had a second casing string, that's provided here as well. Okay, that's not the case here. And then gauge depth is not needed here, but then I specify the lift method, the artificial lift method. And in this case, it's rod pump. And that's what got uploaded here. That's rod pump. So basically, all this manual work that we were trying to do, you can pre-populate the Excel sheet and do it automatically, and that you can do we could do it for one well, but in general, people do it for a set of wells that they're working on. And an example of that Excel sheet pre-populated with all the data for actually 11 wells in the Eagle Ford is provided in our user manual. How you access the user manual, you can click on this at the top right. You can click on this question mark here, user manual. And there you can go into the onboarding on the left. Let me show you that. The onboarding here on the left and mass upload example. And there you have an example with 11 Eagle Ford wells provided from the SPE data repository. And if you download that, we go there, you're gonna see it's a much more difficult file, like much more populated file. Where now here we have 11 wells with their corresponding data, the production data for the 11 wells. This is the one of them. If you scroll down, you're gonna find the second well, etc. Here we go. Second, third well. Here you see the well name. That's there. And then you're going to find the deviation survey data for the different wells. Do this here. There we go. This is the deviation survey data for the different wells. See the well name is changing. And then the wellbore data. Each well will have a corresponding either one configuration or a set of configuration. Like for example, this well has 5 configurations changing with time, and the other wells, most of them have 1 or 2 configurations. Okay, that's how you do it with a mass upload. You can basically mass upload this, and that's what a lot of people do. This is for, let's say if you're working with 20 wells, then generally it's fine to do it with a mass upload. The ultimate solution is to connect through the API. I think I don't have to promote the API anymore because I think practically everyone here is connected to the API. If you're not, then you're really missing out. I have to say it. 90% of the customers that we have are connected through the API. It doesn't cost additional money. Like, don't be afraid. We're not going to charge you more. And it's just a very seamless thing to do. basically your data, your production data gets updated on a daily basis. We connect the API gets connected to your WellView database or any database you have for the wellbore data, and you can calculate bottom hole pressures automatically every single day in the API. So that's it's a very neat thing to have at least. And as I said, if you don't have it, you're seriously missing out, because it doesn't cost anything more, and it just makes your life so much easier. Okay, so that's it from my end. Any questions or comments? Right, and we can wrap it up. Stian or Matthias, do you have any additional comments before we wrap up?
No, nothing here.
Awesome. Okay, thank you everyone. So we'll send the recording of the course just right after the course finishes. Take care.
Thank you, guys.
Thank you.
Thank you. Bye bye.